close your eyes for a moment. Or, if you like, let them grow soft and heavy, your gaze unfocused, drifting. Imagine that you are lying on your back somewhere very still and very dark. Perhaps it is a wide meadow, far from the glow of any city. Perhaps it is the flat top of a desert plateau, warm stone beneath you, the air cool and clean against your skin. The ground holds you completely. You don't need to hold yourself up. You can simply be still and let the earth support every part of you. Above you, the sky has opened up in a way that most of us rarely get to see. There are no clouds tonight. There is no haze. The air is dry and transparent, and the darkness is so deep and so complete that the stars have come out in their thousands, their tens of thousands, pouring across the sky in every direction from horizon to horizon. You feel small beneath this sky, but not in a frightening way, in a restful way, like a child who has been carried and set down gently, held by something much larger and much older than yourself. And there, stretching all the way across the dome of sky above you, is something that looks almost too beautiful to be real. It is a band of soft light, pale and luminous, like a long smear of moonlit cloud that never moves. It arcs from one side of the horizon to the other, crossing the entire sky in a slow, graceful curve. It is faint in some places and brighter in others. In certain patches it seems almost aglow. In other places it breaks apart, interrupted by long, dark rivers of shadow that cut through its heart. This is the Milky Way. This is our galaxy. This is home. What you are seeing, when you look at that soft ribbon of light, is something that took your eyes a moment to understand, but that your ancestors spent their whole lives looking up at in wonder. You are seeing the combined light of billions of stars, not individual pinpoints, though there are plenty of those scattered all around, but the blended, unresolved glow of stars so numerous and so distant that your eye cannot separate them. Each point of that pale light is its own sun, many of them far larger and brighter than our own, but they are so far away, so deeply embedded in the fabric of the galaxy, that they merge together into this gentle, milky luminescence. The name has been with us for a very long time. Across cultures and centuries, human beings have looked up at this ribbon of light and tried to find words for what they were seeing. The ancient Greeks called it Galaxies Kyklos, the Milky Circle. The Romans spoke of the Via Lactea, the Milky Road. In Norse tradition, it was the path walked by the fallen warriors on their way to Valhalla. In many indigenous traditions around the world, it was a river in the sky, a backbone, a seam holding the heavens together. Every name reaches for the same thing, the sense of something continuous, something flowing, something that crosses the entire sky like a path made of soft, scattered light. Let your breathing slow just a little more as we stay here beneath this sky, watching. There is no hurry. There is nowhere else you need to be. The Milky Way is brightest in certain directions, and if you let your eyes travel slowly along its length, you can feel where its heart lies. Follow the band toward the south, toward the rich and complex region where the constellations Sagittarius and Scorpius rise in summer skies. There, the band becomes denser, wider, more luminous. The glow seems to thicken and deepen. That brightness, that concentration of light, that is the direction of the galactic center. That is where the Milky Way is most dense with stars, most rich with ancient suns and drifting clouds of gas, and the invisible machinery of a vast and ancient system. But look more carefully at that bright central region, and you will notice something curious. Even though it is the brightest part of the Milky Way, it is not completely bright. There are dark lanes threading through it, long, irregular shapes where the glow is interrupted, where the light simply stops. These are not gaps in the stars. These are clouds of interstellar dust, enormous and dark, drifting between us and the stars beyond. Dust so dense that it blocks the starlight entirely. casting shadows across the galaxy in a scale almost impossible to imagine. These dark lanes are among the most beautiful features of the Milky Way as seen from the ground, giving the band a layered, textured quality, like paint applied in careful strokes across a dark canvas. The galactic center itself lies hidden behind these dust clouds. Astronomers know it is there. They have measured it, mapped it, studied it with great patience and extraordinary ingenuity. But they cannot see it with ordinary light, because the dust between us and the center is simply too thick. Thousands of light years of drifting interstellar dust, accumulated over billions of years, stand between our eyes and the heart of our galaxy. It is as though you were looking at a beautiful painting through layer after layer of frosted glass. And so astronomers have learned to look in other ways. Infrared light, which is longer wavelengths than visible light, can pass through the dust more easily, and infrared telescopes have revealed the hidden structure of the galactic disk and bulge. Radio waves pass through the dust as though we're not there at all, and radio telescopes have mapped the motions of gas clouds deep inside the galaxy. With these tools, scientists have slowly built up a picture of a place they can never see with their own eyes. A picture of the galactic center, bustling with ancient stars, swirling with gas, harboring at its very heart one of the most extraordinary objects in the known universe. But we will come to that in time. For now, let the dust be mysterious. Let the dark lanes be beautiful. There is something to be said for a mystery that teaches you to look in new ways. There is one more thing worth noticing as you lie here beneath this sky, and it is something that sounds simple, but has a depth to it that can take a lifetime to fully absorb. Every single star you can see with your naked eye tonight, every bright, individual point of light in this sky, regardless of where it appears, is part of the Milky Way. The bright stars near the horizon, the faint ones scattered between, the prominent clusters, the solitary wanderers, all of them are suns within our own galaxy, all of them members of the same vast rotating system of which our own sun and our own Earth are a part. We live inside the Milky Way. We are not observers watching from the outside. We are embedded within it, partway along one of its curving arms, riding in slow orbit around a distant center we cannot directly see. This is why the galaxy appears as a band across our sky, rather than as the beautiful spiral we might imagine from above. We are inside the disk looking outward, the way you might lie inside a vast, flat city and see the skyline rising all around you on every side but be unable to see the city's shape from within. The Milky Way surrounds us completely. It has always surrounded us. It always will. This is one of the great challenges that astronomers face when studying our galaxy. We cannot step outside of it. We cannot get a clear, bird's-eye view. We must work out the shape and structure of our home from within it, using the light and motion of the stars around us as our clues, the way you might try to draw a map of a forest you have never left. Modern surveys of the sky have helped enormously. Missions that measure the precise positions and motions of billions of stars have transformed our understanding. But there is still something humbling and beautiful about the fact that we know less about the shape of our own galaxy than we know about some galaxies millions of light years away. The most familiar home is sometimes the hardest one to see clearly. So let that thought settle quietly into you, like water soaking slowly into warm ground. You are here on a small world beneath a great sky, looking up at the light of 100 billion suns. The band of the Milky Way stretches above you from edge to edge of the horizon, vast and soft and ancient. The dark dust lanes curl through it like the courses of hidden rivers. The center glows somewhere behind those veils of dust, beyond your sight, but not beyond your knowing. And all of it, every light, every shadow, every dark lane and glowing patch, is part of the galaxy that made you, that contains you, that you are in the most literal and profound sense of the word a part of. Let your body be heavy. Let your thoughts grow slow. The sky above you is enormous and patient, and it has been here for billions of years, and it will be here long after tonight has passed. There is nothing you need to do right now but rest and breathe and let the ancient light fall gently down upon you. We're just beginning our journey through this magnificent galaxy. There is so much more ahead. The structure of its arms, the nature of its center, the dark matter that holds it all together, the ancient clusters of stars that orbit its edges, and the long, slow story of how this galaxy came to be and where it is going. But for now, in this first quiet chapter, simply be here beneath the sky and let the Milky Way be what it has always been. A river of soft light across the darkness, beautiful and vast, ancient and alive, and completely, intimately yours. Let yourself settle a little deeper now. If you have found a comfortable position, there is no reason to move. Let your limbs be heavy, your shoulders soft, your jaw unclenched. The air around you is still, and somewhere above you, whether you can see it tonight or not, the Milky Way continues its slow, silent arc across the sky. Billions of stars in slow, patient orbit. The whole vast system turning like a wheel so enormous that a single rotation takes hundreds of millions of years. In this chapter, we're going to spend some time simply getting to know our galaxy in the most fundamental way. Not its details, not its mysteries, but its basic nature. What kind of thing is the Milky Way? What is it made of? How old is it? Where does it fit in the grand scheme of the universe? These are quiet questions, gentle questions, the kind you might ask about a place you have lived your whole life but never quite stopped to fully understand. And the answers, when you hold them softly in your mind, have a way of making the night feel even more immense and even more peaceful. The Milky Way is, at its most fundamental level, a galaxy. That word, galaxy, comes from the ancient Greek word for milk, a reminder that long before anyone understood what it truly was, human beings recognized the Milky Way as something unique and luminous in the sky above them. A galaxy is a vast system of stars, gas, dust, and a mysterious invisible substance called dark matter, all bound together by gravity into a single, coherent structure. Galaxies are the basic units of the large-scale universe. They come in a variety of shapes and sizes. Some are irregular and chaotic, some round and smooth, some swept into elegant spirals. And they are scattered throughout the observable universe in numbers so large they become almost meaningless to contemplate. Estimates suggest there are hundreds of billions of galaxies, perhaps more. And among all of these, the Milky Way is our home. More specifically, the Milky Way is classified as a barred spiral galaxy. If you could somehow lift yourself far above the galactic plane and look down at our galaxy from a great distance, the way you might look down at a city from an airplane, watching the patterns of its streets emerge from chaos, you would see a broad, flat disk of stars sweeping outward in graceful spiral arms. At the center of this disk, instead of a simple round knot of stars, you would see something more distinctive, a long, bright bar of densely packed stars cutting straight across the core, like a line drawn through the galaxy's heart. The spiral arms emerge from the ends of this bar, curling outward into space in long, sweeping curves. This bar is one of the Milky Way's defining features, and it gives our galaxy its more precise classification, SBBC. These letters might sound like a technical code, and in a sense they are, a shorthand that astronomers use to describe the shape and character of a galaxy in just a few characters. The S stands for spiral. The B indicates that the galaxy has a bar. The BC at the end describes how tightly the spiral arms are wound and how prominent the central bulge is. A galaxy classified as BC has moderately open arms and a moderately sized bulge, not too tightly coiled, not too loosely flung. In this respect, the Milky Way is a fairly typical large spiral galaxy, though of course to us it is anything but typical. Let that image drift through your mind for a moment. A great flat disk, slowly turning in the dark. Long arms of stars and gas curling outward from a bright bar at the center. The whole structure embedded in a faint, spherical cloud of older stars and dark matter. This is the shape of home. This is the architecture of the place where every human life has ever been lived, where every story has unfolded, where every mountain and ocean and autumn leaf has existed. All of it contained within this quietly spinning structure in space. The Milky Way is considered a large galaxy. In the cosmic neighborhood, there are galaxies far smaller than ours. Tiny dwarf galaxies containing only a few million stars, scattered like satellites around the larger ones. And there are galaxies larger than ours, enormous elliptical giants containing trillions of stars, their shapes smooth and featureless compared to the intricate beauty of a spiral. But the Milky Way sits comfortably among the large spirals, a substantial and well-developed galaxy by any measure. How many stars does it contain? This is one of those questions that sounds simple, but leads quickly into a kind of comfortable bewilderment. The honest answer is that we are not entirely sure. Counting every star in our own galaxy is a task of almost incomprehensible difficulty, for reasons we will explore more deeply in later chapters. But current estimates suggest the Milky Way contains at least 100 billion stars. 100 billion. That number is so large it loses its meaning almost immediately, the way very large numbers tend to do. But try, for just a moment, to feel its weight. If you spent 1 second appreciating each star in our galaxy, just 1 second per star, it would take you more than 3,000 years to get through them all. And that is just for our galaxy, one of hundreds of billions. Some estimates put the number even higher. Several 100 billion stars, perhaps more, once you account for the faint, dim stars that are difficult to detect. The true total may be something we never know with precision. But the galaxy is full. It is crowded with suns, most of them unseen from Earth, most of them unknown to any human mind, each of them a world unto themselves with their own rhythms and energies, and, perhaps, their own stories. And this galaxy of 100 billion or more stars is old. Deeply, profoundly old in a way that quietly reshapes your sense of time if you let it. The Milky Way is approximately 13.6 billion years old. To put that in perspective, the universe itself is estimated to be about 13.8 billion years old. Our galaxy formed not long, astronomically speaking, after the Big Bang itself. In the first few 100 million years after the universe began, the conditions were already right for the Milky Way to start taking shape. Clouds of gas collapsing under gravity, the first stars igniting, the first structures of what would eventually become our galactic home beginning to emerge from the early universe's churning, chaotic expansion. 13.6 billion years. That means the Milky Way has been here for most of the universe's existence. It was already old when our sun formed, about 4.5 billion years ago. It was already ancient when the first simple life appeared on Earth. It existed long before the planets of our solar system, long before the rocks of our continents, long before any of the elements in your body had been forged in the hearts of stars and scattered into the cosmos. You are, in a very real sense, made of material that has been part of this galaxy for billions of years. Atoms that were once in other stars, other clouds of gas, other places entirely within this vast and ancient system. There is something deeply restful about this kind of oldness. Not the oldness of things that are worn out or decayed, but the oldness of things that have proven themselves, things that have endured through change and upheaval and still remain, still function, still hold together. The Milky Way has survived for almost the entire life of the universe. It has seen the birth and death of generations of stars. It has incorporated the remnants of smaller galaxies that fell into it long ago. It has changed, evolved, grown more complex over time, and yet it persists, turning slowly in the darkness, star after star after star, generation after generation, continuing. The Milky Way is, in the language of astronomers, typical of large barred spiral galaxies. It is not the most extreme galaxy. It is not the most massive, not the most luminous, not the most unusual. In many ways, it is an ordinary member of a common class of objects, and there is something comforting in that ordinariness. Our home galaxy is not exceptional in the way that superlatives tend to be exciting. It is exceptional in the way that a good and well-lived life is exceptional, not because it towers above all others in some dramatic way, but because it has developed its own deep complexity, its own history, its own character, its own quiet beauty. Astronomers study the Milky Way partly because it is our home and we want to understand it, and partly because it serves as a template, a detailed, close-up example of how a large spiral galaxy works, develops, and evolves over cosmic time. What we learn about the Milky Way helps us understand the hundreds of billions of other spiral galaxies out there in the universe. Galaxies so far away that we can only see their broad outlines, never their individual stars. In this way, our galaxy is both a subject of study and a teacher, a close, detailed example that illuminates something much larger. So let all of that settle gently into you now. The Milky Way is a barred spiral galaxy, one of hundreds of billions. It contains at least 100 billion stars, possibly more. It is 13.6 billion years old, nearly as old as the universe itself. It is large but not extreme, complex but not chaotic, ancient but still active and alive. It is home to our sun, to our solar system, to our world, to every living thing that has ever existed. And it has been here, patient and vast, for most of the time that anything has been here at all. You are part of something that began nearly 14 billion years ago. That thought can live gently in you as you breathe, as your body grows heavier, as the night deepens around you. There's a long history beneath you and above you, and you are somewhere inside it, small and warm and resting. The galaxy turns, the stars hold their courses, and you are here quietly, in the middle of all of it. Rest now. We will continue our journey soon. If you have been resting comfortably, stay just as you are. Let your body continue to sink a little deeper into whatever surface holds you. The stillness around you is not emptiness. It is full of things too vast and too quiet to hear. Things moving in long, slow rhythms that your body could never feel, but your mind can begin to gently reach toward. We're going to talk now about where we are. Not just on Earth, not just in our solar system, but in the great sweep of the Milky Way itself. Where do we live inside this galaxy of 100 billion stars? The answer, when you first hear it, might feel a little anticlimactic. We are not at the center. We are not near a spectacular spiral arm junction, or on the very edge, or in some particularly distinguished or dramatic location. We are, in a way that most inhabitants of large things tend to be, somewhere in the middle regions. Not central, not peripheral, but comfortably situated in the broad, star-rich disk of the galaxy, in a quiet neighborhood that has proven, over billions of years, to be a very good place for a solar system like ours to exist. More precisely, our sun lies within the galactic disk, the flat, rotating plane of stars that makes up the main body of the Milky Way. And within that disk, our sun is located approximately 26,000 light-years from the galactic center. 26,000 light-years. Light, which travels at nearly 300,000 kilometers every second, so fast that it can circle the entire Earth more than 7 times in a single second. It takes 26,000 years to make the journey from where we are to the heart of our galaxy. That distance is almost beyond intuition, and yet within the context of the Milky Way, which stretches roughly 100,000 light-years from edge to edge, We are positioned somewhere in the middle reaches, not crowded into the dense, ancient core, not stranded at the galaxy's thin outer rim, somewhere between in the inhabited middle. Our sun resides in a region called the Orion Arm, sometimes known as the Orion Spur. The name comes from the constellation Orion, which lies in this part of the sky and whose associated nebula. One of the most famous star-forming regions visible to the naked eye is part of this same galactic feature. The Orion Arm is not one of the Milky Way's major spiral arms. It is a smaller, shorter structure, a spur, as the name suggests, that bridges the space between two of the larger arms. Our sun and the stars around us inhabit this modest spur, tucked in a quieter zone between the grander Perseus arm on one side and the Scutum Centaurus arm on the other. There is something characteristically humble about this. We are not at the grandest address in the galaxy. We are on a spur between major arms, in the middle reaches of a disk, orbiting a fairly ordinary star. And yet from here, life has emerged. From here, curiosity has arisen. From here, someone is listening to the story of the galaxy that contains them, drifting gently towards sleep on a quiet night. The universe does not seem to require grandeur as a precondition for meaning. Now, the sun does not simply sit still within the Orion Arm. Everything in the galaxy is in motion. Everything orbits. Everything participates in the great slow turning of the galactic disk. Our sun orbits the center of the Milky Way, just as the Earth orbits the sun. But the scale is so much larger that the motion feels, from our perspective, like no motion at all. The sun's orbit around the galactic center takes approximately 200 million years to complete. Astronomers have given this vast interval of time a name, the galactic year, sometimes also called a cosmic year. One galactic year is 200 million Earth years. Think of what has happened on Earth in just the last 200 million years. The supercontinent Pangaea was only beginning to break apart. The first dinosaurs were just emerging. The Atlantic Ocean did not yet exist. In the time it takes our sun to complete a single orbit around the galactic center, everything about the surface of our planet, its continents, its oceans, its life, can be transformed beyond recognition. And yet for the galaxy, that is simply one turn of the wheel. Our sun has completed this journey approximately 20 times over the course of its lifetime so far. The sun's orbit around the galactic center is not a perfect circle. It traces a path that is roughly circular, but not precisely so. And this is common for stars in the galactic disk. The disk is not a perfectly smooth and ordered place. It is structured, yes, but also textured with concentrations of matter, variations in gravity, the sweeping density waves of the spiral arms themselves. As a result, our sun's orbit carries it gently in and out of the galactic disk's features over time, sometimes passing closer to a spiral arm, sometimes drifting a little farther from one. And there is another motion layered on top of the orbital one. As the sun travels around the galaxy, it also oscillates. It bobs gently up and down through the plane of the galactic disk, like a horse on a carousel that rises and falls as it turns. At any given point in its orbit, the sun is either slightly above the midplane of the disk, or slightly below it, or passing through it on its way from one side to the other. The amplitude of this bobbing motion is relatively modest, but it means that over hundreds of millions of years, the sun has repeatedly crossed back and forth through the galactic plane, periodically spending time in the denser regions near the midplane, and then rising or sinking away from it. This oscillation has been studied and debated as a possible factor in the long-term history of life on Earth. The galactic plane is where the density of stars, gas, and dust is highest, and where encounters with large molecular clouds, or proximity to energetic events like supernovae, are more likely. Whether these periodic crossings of the galactic plane have left any signature in the fossil record or the history of extinctions on Earth is a question that researchers have explored with great interest and some disagreement. The connection, if it exists, is subtle and difficult to establish. But the question itself is remarkable. Could the rhythms of our galaxy have shaped the history of life on our planet? The cosmos and the living world, linked by the slow beating of a galactic clock. Wherever the sun is in its orbit at any given moment, it is accompanied by everything in our solar system. All 8 planets, all their moons, the asteroid belt, the distant icy bodies of the outer solar system, and of course our small, blue world. Everything travels together. The sun carries us along in its great slow circuit around the galactic center, and we are passengers who will never feel the journey. In our short human lives, in our long human history, we move an almost imperceptible fraction of a single galactic orbit. The arc of our path is too vast, and the motion too slow for any human sense to detect. And yet we know we are moving. We know it from the slight shift in the positions of nearby stars compared to distant ones. We know it from the mathematics of gravity and orbital mechanics. We know it from the careful measurements of observatories that have tracked the motions of stars for decades, building up a picture of the galaxy's rotation that no single human lifetime could have gathered. We know we are moving the way you might know a ship is sailing, even when the sea around you seems completely still, not from the feeling of motion, but from the careful reading of the stars. Every visible star you can see in the night sky is part of this same rotating system. They are all moving, all following their own orbits around the galactic center, all participating in the great turning of the disk. When you look up at the sky on a clear night and see those points of light scattered across the darkness, what you are seeing is not a static backdrop, but a dynamic, moving community of stars. Each one a sun, each one on its own long journey around the galaxy, all of them neighbors in this slowly rotating wheel of light. We are all going around together. The stars of the night sky and our own sun, the Orion Arm and the great spiral arms beyond it, the dense core and the thin outer reaches, all of it turning slowly and immeasurably in the dark of space. And we are here, on one small planet orbiting one unremarkable star in one quiet corner of one arm of the galaxy, carried along by the motion we cannot feel, part of a journey that will outlast every civilization that has ever existed and every one that ever will. Let that carry you for a moment. Let the motion you cannot feel become a kind of comfort. You're not still in the universe. Nothing is still. But the motion is so vast, so slow, so perfectly balanced that it feels like rest. The galaxy turns. The stars hold their relative positions in the sky. The night is quiet around you. And somewhere in the long, slow arc of 200 million years, you are here, breathing gently, resting on this world, riding the galactic carousel in perfect, imperceptible peace. Sleep is nearby. Let it come closer. We will continue our exploration when you are ready. Let your breathing be easy. Let each exhale carry a little more weight out of your body, a little more tension, a little more of the day's accumulated noise. You're somewhere quiet and dark and still. The universe goes on around you in every direction. And we're going to spend some time now simply considering the shape of the place that contains us, the size and the structure of the Milky Way, the basic geometry of our galactic home. If you try to describe the Milky Way's shape to someone who had never seen it or heard of it, you might reach first for something familiar. A disk, you might say, like a coin, but much, much thinner in proportion to its width. Or like a vinyl record, those flat black circles that play music, wide across their face, thin at their edges, with a slightly raised area in the center. The Milky Way is something like that, a great flat disk of stars, thin and wide, with a bulging central region where stars cluster most densely, and long arms spiraling outward through the disk. The disk itself stretches approximately 100,000 light-years from one side to the other. 100,000 light-years. We have already touched on the idea of a light-year as a unit. The distance light travels in 1 year. moving at nearly 300,000 kilometers per second. 1 light year is just under 10 trillion kilometers. 100,000 light years is 10 quintillion kilometers, a number so large it simply becomes a sound, a word, with no real grip on the imagination. But the disk of our galaxy spans that distance. If you could somehow fly from one edge of the galactic disk to the other at the speed of light, the fastest anything in the universe can travel, the journey would take 100,000 years. And yet, for all its tremendous width, the disk is remarkably thin. Near our Sun, which is a fairly typical location in the disk, the galactic disk is only about 1,000 light-years thick. 1,000 light-years of depth, compared to 100,000 light-years of width. That is a ratio of 1 to 100. If you scaled the Milky Way's disk down to the size of a standard dinner plate, about 30 centimeters across, it would be only about 3 millimeters thick, thinner than a stack of a few pages of paper. The Milky Way is, in a very real geometric sense, an enormously flat structure. It is far flatter, proportionally speaking, than almost anything we make or encounter in daily life. This extreme flatness tells us something important about the galaxy's history and dynamics. Disk galaxies form this way because of rotation. As a great cloud of gas collapsed in the early universe to form what would become the Milky Way, it was already slowly spinning. Gravity pulled the gas inward, but angular momentum, the tendency of rotating things to resist collapsing in the plane of their rotation, allowed the gas to settle into a flat disk instead of a sphere. Stars formed within this disk, and because they formed from material that was already rotating in the same direction, they tend to orbit in the same plane, maintaining the disk structure over billions of years. The flatness of the galaxy is the signature of its rotation, written in the positions of 100 billion stars. At the center of the disk, things are different. Instead of the thin, flat structure of the outer disk, the galactic center features a bulge, a roughly spherical concentration of stars that swells out of the plane of the disk in both directions, like a lens or a slightly flattened ball sitting at the center of the record. This central bulge spans approximately 10,000 light-years. It is rich with old stars, many of them billions of years older than the Sun, stars that formed in the early life of the galaxy when the density of gas in the central regions was highest and star formation proceeded most rapidly. The bulge is dense, bright, and ancient, a kind of living archive of the galaxy's earliest chapters. Surrounding the disk and the bulge, extending far out into space in every direction, is a much more diffuse structure called the stellar halo. The halo is not a disk. It is roughly spherical, enveloping the galactic disk like a vast, nearly transparent sphere. And it is enormous. The stellar halo extends several 100,000 light-years outward from the galactic center, meaning it reaches far beyond the visible disk, into regions of space where stars become increasingly sparse and the darkness between them grows vast. If the disk is the city, the halo is the surrounding countryside, thinly settled, stretching on much farther than the city lights suggest. The stars of the halo are very different from the stars of the disk. They are old, many of them among the oldest stars in the galaxy, relics of the earliest periods of galactic formation. They are also metal-poor, meaning they contain very little in the way of elements heavier than hydrogen and helium. This is a signature of their age. In the early universe, before many generations of stars had lived and died and scattered heavier elements through space, the raw material for new stars was nearly pure hydrogen and helium. The halo stars formed from this early, unenriched material, and they carry that chemical simplicity as a kind of birth certificate, proof of their ancient origins. Now here is something that adds a beautiful layer of complexity to the picture. The disk of the Milky Way is not perfectly flat. It is warped. If you could look at the galactic disk edge-on, as you might look at a dinner plate from the side, you would see that the outer edges do not lie in a perfectly straight plane. One side of the outer disk bends gently upward, curving above the midplane. The opposite side curves in the other direction, bending below the midplane. The overall shape is something like a very gently twisted or bent disk, with the warp becoming more pronounced toward the outer edges. The origin of this warp is still a topic of active research and scientific discussion. One prominent idea is that it is caused by the gravitational influence of the Milky Way's satellite galaxies, the Large and Small Magellanic Clouds, which orbit our galaxy at a distance, and whose gravity tugs on the outer disk, pulling it gently out of the plane over time. Another possibility involves the dark matter halo that surrounds the galaxy, which may itself be slightly tilted relative to the disk, exerting a gravitational influence that tilts the disk in response. Whatever the cause, the warp is real, measurable, and a reminder that even the broad structure of our galaxy is not perfectly simple. It has been shaped by forces and interactions across its long history. The disk also flares. As you move from the inner regions of the galaxy outward toward the edges, the disk gradually becomes thicker, not thinner, as you might expect for a structure that seems to fade out toward the edges, but physically thicker in the sense that the distribution of stars spreads over a greater vertical range. This flaring is likely due to the decrease in the gravitational force holding stars in the plane of the disk as you move farther from the galaxy's concentrated center. With less gravity to keep them confined to the thin midplane, stars in the outer disk are free to wander a little more widely above and below it. So the complete picture of the Milky Way shape is something like this: a wide, flat, gently warped and flaring disk of stars, 100,000 light-years across, and perhaps 1,000 light-years thick near our position. At the center of the disk, a bulge of old stars, dense and ancient. Surrounding all of this, a vast spherical halo of very old, metal-poor stars, extending hundreds of thousands of light-years into space. And beyond even the stellar halo, though we will explore this more later, an even larger and more diffuse halo of dark matter, the invisible substance whose gravity holds the entire galaxy together. This is the shape of the vessel that carries us. Not a simple sphere, not a perfect disk, but something more textured and interesting, warped and flaring at its edges, centrally bulging, haloed in old stars and invisible matter, the whole structure slowly rotating, slowly evolving, slowly breathing in the deep time of cosmic history. There is something almost meditative about contemplating a shape this large. The mind reaches toward it and finds it cannot fully grasp it, and after a moment of that reaching, the mind tends to grow quiet. It is a good kind of quiet, the kind that comes when you've tried your best to understand something much larger than yourself and have arrived at a gentle, accepting wonder instead. The galaxy is bigger than you can hold in your mind, and that is all right. You are inside it anyway, held by it, part of its motion and its story, whether you can picture it clearly or not. Let your thoughts drift now, like stars in the outer halo, widely spaced, moving slowly, each one on its own long path through the dark. There is no hurry. The galaxy will be here when you wake, and when you sleep, and in all the long years between. It has been here for 13.5 billion years, and it is not going anywhere. You are safe inside its vast, flat, slowly turning shape. Rest. We will explore further when you are ready. Stay with me as we continue drifting through the galaxy together. If your eyes are heavy, let them be heavy. If your breathing has slowed, let be slow. We are not in a hurry. The Milky Way has been here for 13.5 billion years, and it will wait for us while we rest. But if part of your mind is still awake and listening, let it follow these words gently, the way water follows the shape of the land it flows across, not forcing anything, just moving along the natural contours of the story. In the last chapter, we traced the broad shape of the Milky Way, the flat disk, the central bulge, the surrounding halo. Now we're going to look a little more carefully at the distinct structural layers that make up our galaxy. Astronomers have found it useful to think of the Milky Way as being composed of 6 main structural components, each with its own character, its own population of stars, its own role in the galaxy's life and history. Understanding these components is like understanding the different rooms and neighborhoods of a vast city. Each one has its own feel, its own history, its own kind of inhabitant. At the very heart of the galaxy lies the nucleus. This is the innermost region, the dense, bright core at the center of everything. The nucleus contains the highest density of stars anywhere in the Milky Way. Stars packed so closely together that if you lived on a planet near the galactic center, your night sky would blaze with thousands of bright stars, never truly dark, the sky itself luminous with their collective light. The nucleus is also the home of Sagittarius A*, the supermassive black hole that anchors the entire galaxy, which we will visit in a dedicated chapter later in our journey. For now, simply imagine the nucleus as a blazing, crowded, ancient place at the center of our galaxy, dense with stars, rich with energy, one of the most extreme environments in the known universe. Surrounding the nucleus is the central bulge, that roughly spherical swelling of stars we encountered in our last chapter. The bulge is composed mostly of older stars, not ancient halo stars, but mature, well-developed stars that formed early in the galaxy's history when the central regions were dense with gas and star formation was rapid and vigorous. The bulge stars are redder and cooler than the young blue stars found elsewhere in the galaxy, and they move in complex, somewhat chaotic orbits compared to the orderly circular orbits of stars in the disk. The bulge is dense and luminous, and it glows with the warm, amber light of old age, a city center built long ago and still inhabited by those who have been there from the beginning. Next comes the thin disk, and here the character of the galaxy changes dramatically. The thin disk is where the galaxy's ongoing life happens. It is where most of the gas and dust resides, where giant molecular clouds drift slowly through space, where new stars are being born right now from collapsing clouds of cool gas. The thin disk contains the spiral arms, those sweeping concentrations of stars and gas that give spiral galaxies their beautiful, recognizable form. It is where young, hot, blue stars blaze brightly for their short and brilliant lives, where star clusters form and gradually disperse their members into the general stellar population, where the raw materials of future solar systems drift in vast, cold clouds. The thin disk is also, of course, where our sun lives. We are inhabitants of the thin disk, and the thin disk character, its mix of young and old stars, its ongoing star formation, its spiral structure, is part of what makes our neighborhood in the galaxy relatively dynamic and active compared to, say, the old and settled bulge. The thin disk shows a wide range of stellar ages, from ancient stars billions of years old to infant stars only millions of years into their lives, all mixed together in the same rotating plane. This diversity is a sign of a place that has been continuously productive, continuously creating for most of the galaxy's history. Sitting just above and below the thin disk is a component called the thick disk. The thick disk is puffier than the thin disk, extending farther above and below the galactic plane. It contains stars that are older and chemically different from those in the thin disk. Thick disk stars formed relatively early in the galaxy's history, perhaps in a burst of star formation during the first few billion years, and they carry a different chemical signature. Specifically, they are enhanced in what astronomers call alpha elements, such as oxygen, magnesium, and calcium, compared to iron. This chemical difference reflects the different pace of their formation. When the thick disk stars were being born, the galaxy was enriching its gas very rapidly through a high rate of massive star deaths. And the alpha elements from those stellar explosions accumulated faster than the iron that comes from a different type of supernova that takes longer to produce. The thick disk is, in a sense, a fossil layer. It records a particular era in the galaxy's life, a time of rapid, vigorous star formation that has since settled into the more measured pace of the thin disk. Studying the thick disk is like reading a chapter of the galaxy's autobiography, written in the compositions of stars that formed during that early, energetic period. Beyond the disk entirely, above and below, and all around it, lies the halo. We met the halo briefly in our last chapter, but now we can appreciate it as a structural component with its own distinct character. The halo hosts old stars, including many of the oldest in the entire galaxy, and it is also home to the globular clusters, dense spherical collections of hundreds of thousands to millions of stars, each cluster like a miniature galaxy in itself, orbiting the Milky Way on long, looping paths that take them far out into the halo and then swinging back and toward the galactic center. The globular clusters and the halo stars are the galaxy's oldest residents, and their chemistry and ages provide some of the clearest windows we have into the Milky Way's earliest history. These 6 components, the nucleus, the bulge, the thin disk, the thick disk, the spiral arms within the disk, and the halo, are not sharply separated. They blend into one another in gradations, their boundaries fuzzy and transitional rather than hard and clear. Real galaxies are not assembled from prefabricated parts with clean edges. They grow and evolve, and the components we identify are patterns in that growth, regions where certain properties of stars and gas cluster together in recognizable ways. What is remarkable about this structure is how much information it contains. Each component is not just a collection of stars. It is a record of a particular epoch in the galaxy's history. The halo and the globular clusters remember the very early universe, before the disk had fully formed. The thick disk remembers a period of rapid, intense star formation. The thin disk records the long, ongoing story of more gradual enrichment and evolution. The bulge carries the memory of the dense, early center. The nucleus holds the most extreme conditions the galaxy has ever produced. All of this history is written in the stars themselves, in their ages and compositions and orbital motions, waiting to be read by astronomers patient and skilled enough to interpret it. Think for a moment about what it means to live inside this layered, historical structure. You are not just in a galaxy. You are in a specific layer of a galaxy, the thin disk, at a specific position within that layer. You are surrounded by a particular mix of young and old stars, by drifting clouds of gas and dust, by the ongoing business of star formation and stellar evolution. Beneath you, in a metaphorical sense, are layers that reach back deeper and deeper into cosmic history. Above and below the plane of the disk, the halo extends outward with its ancient stars and globular clusters, carrying memories of the galaxy before you existed, before the Earth existed, before the solar system had formed. There's a kind of richness to this that is easy to miss. We tend to think of space as empty, as a featureless dark void punctuated by bright objects. But the galaxy is not empty. It is full of structure, full of history, full of distinct regions, each with their own character and their own story. You are living inside one of the most complex and richly structured objects in the universe, and the complexity reaches right down to the neighborhood you inhabit. Let that sense of richness stay with you as you breathe. You are inside something layered and ancient, something with a history that stretches back nearly to the beginning of the universe. The disk hums with star formation around you. The halo holds its ancient stars in quiet orbits far overhead. The nucleus blazes at the galaxy's heart, far away and unseen, but real, always real. You are not floating in emptiness. You are resting inside a structure of extraordinary complexity and beauty, cradled by the thin disk of the Milky Way, surrounded by the unfolding story of a 13-billion-year-old galaxy. And right now, in this chapter of that long story, you are here, breathing, resting, drifting towards sleep. Let the galaxy hold you. Let its ancient structure be a kind of comfort. Everything is in its place. Breathe in slowly, and breathe out slowly. Let the rhythm of your breathing be easy and natural, like a tide moving in and out against a quiet shore. We are going on a gentle journey through the most visually striking features of the Milky Way: the spiral arms that sweep through its disk, and the great bar of stars that cuts across its center. These are the structures that, if you could see our galaxy from far above, would make it instantly recognizable as the kind of beautiful, sweeping spiral you might see in photographs of distant galaxies. They are the galaxy's most dramatic architecture, and tonight we will trace their shapes together in the quiet dark. The disk of the Milky Way is not uniform. It is not a smooth, featureless sheet of stars, all evenly distributed across 100,000 light years. Instead, it is organized, structured into lanes and concentrations, into regions of higher and lower density, into the distinctive sweeping curves we call spiral arms. These arms are the galaxy's most famous features, and yet they are also, in a subtle way, one of its most misunderstood ones. When most people picture a spiral arm, they might imagine something like a solid physical structure, a ribbon of material attached to the galaxy and rotating with it, the way the blades of a fan rotate together as a unit. But spiral arms are not quite like that. Spiral arms are more like waves. They are regions of higher density that move through the disk, somewhat independently of the individual stars themselves. Imagine a busy highway at rush hour where traffic slows and bunches up near a bottleneck, a long stretch of denser, slower-moving cars, and then disperses again once past the congestion point. The traffic jam itself seems to move or remain in a location, even as individual cars pass through it and emerge on the other side. A spiral arm works somewhat similarly. Stars, gas, and dust enter the arm from one side, slow down and pile up in the denser region, and then emerge from the other side and continue their orbits. The arm itself persists as a feature even as the material within it gradually changes. This has an important consequence for star formation. When gas clouds enter a spiral arm and are compressed by the arm's higher density, the compression can trigger the collapse of those clouds into new stars. This is why spiral arms tend to be bright with young, hot, massive stars, stars that formed within the arm relatively recently, and that burn so brightly they are visible across great distances. The blue-white brilliance of young massive stars lights up the spiral arms, making them stand out visually even against the background of older, dimmer stars in the rest of the disk. Star formation is especially active in spiral arms, and the arms serve as the galaxy's most productive stellar nurseries. The Milky Way has several spiral arms, though their exact number and configuration is still a subject of ongoing research and refinement as new surveys provide more detailed maps of our galaxy structure. Two of the most prominent are the Perseus arm and the Scutum Centaurus arm. The Perseus arm lies on one side of our Sun's position in the galaxy, relatively nearby in galactic terms. The Scutum Centaurus arm lies on the other side, sweeping through the inner regions of the galaxy and curving around toward the central bar. These two major arms bracket our own modest Orion spur, the smaller feature that our Sun calls home. Each arm has its own character, its own population of star-forming regions, its own bright nebulae where new stars are igniting. If you were a traveler passing through the galaxy over millions of years, you would experience each arm as a kind of stellar city, denser, brighter, more active than the quieter regions between the arms. You would encounter more giant molecular clouds, more young star clusters, more of the raw material and fresh products of stellar birth. And then, as you drifted past the arm and into the interarm region, the density would thin, the brightness would fade, and you would find yourself in the quieter countryside between galactic cities. Now, let us travel to the center of the disk, where the spiral arms connect to something even more striking. At the heart of the Milky Way's disk, instead of a simple spherical concentration of stars, there is a bar, a long, elongated structure of densely packed stars that stretches straight across the inner region of the galaxy. If you imagine a child's drawing of a galaxy as a circle with curved lines spiraling outward from the center, and then imagine drawing a straight line through the middle of that circle, connecting the two sides where the spiral arms emerge, that is roughly the geometry of the central bar. The Milky Way central bar is an enormous structure. It stretches across the inner portion of the galaxy, and the spiral arms emerge from its two far ends, curling outward into the disk from the tips of the bar rather than from a single central point. This is what gives the Milky Way its classification as a barred spiral galaxy, rather than a simple spiral. The arms are bar-connected, born from the ends of this great linear feature rather than winding directly from the nucleus. What is the bar made of, and why does it exist? The bar is composed of stars, billions of them, moving in elongated, coordinated orbits that collectively maintain the bar's shape over time. The stars are not all moving in the same direction simultaneously, which might cause the bar to quickly fly apart. Instead, they move in carefully choreographed elliptical orbits that, on average, collectively sustain the elongated shape. It is a kind of stable pattern maintained by the collective behavior of billions of individual stars, the way a murmuration of starlings maintains a coherent, beautiful shape while each bird follows simple local rules. The bar plays an important role in the galaxy's internal dynamics. One of its most significant functions is to funnel gas from the outer disk toward the inner regions of the galaxy. Gas moving through the disk can become caught up in the bar's gravitational influence and redirected, channeled along the bar's length toward the center. This inflow of gas feeds the central regions with fresh material, which can in turn fuel star formation in the central regions, and, crucially, provide material that can eventually fall all the way to the very center, feeding the growth of the supermassive black hole that sits at the galaxy's heart. In this way, the bar acts somewhat like a conveyor belt or a river channel, gathering material from a wide area of the disk and directing it inward. This makes the bar not just a passive structural feature, but an active participant in the galaxy's ongoing evolution. The rate at which gas flows inward along the bar can influence how quickly stars form in the central bulge, how actively the central black hole feeds, and how the overall character of the inner galaxy evolves over time. There is a wonderful complexity to the relationship between these structures. The bar, the arms, the disk, the bulge. They are not independent features. They interact with each other, influence each other, shape each other's behavior over long periods of time. The bar drives gas toward the center. The spiral arms trigger star formation in the disk. The new stars formed in the arms eventually age, die, and scatter their materials back into the interstellar medium, enriching the gas clouds that will form the next generation of stars. The whole system is dynamically connected, each component affecting and being affected by the others in a great, slow, intricate conversation that has been going on for billions of years. Lying here in the quiet, it is perhaps difficult to feel any of this. The galaxy does not announce its structure to us on human timescales. The spiral arms do not visibly move. The bar does not obviously funnel gas. The arms do not glow with a light bright enough to see from our position inside the disk. All of this beauty and dynamism is hidden from our direct perception, revealed only through patient observation, careful measurement, and the disciplined imagination of science. But it is real. It is happening, right now, as you breathe and rest. Somewhere in the Perseus arm, a young star cluster is illuminating a vast nebula with its brilliant new light. Somewhere along the central bar, a cloud of gas is flowing inward, drawn by the bar's collective gravity toward the inner galaxy. Somewhere in the Scutum Centaurus arm, new stellar nurseries are collapsing, new suns beginning their ignition, new worlds perhaps beginning to form around them in disks of gas and dust. The galaxy is alive with process and change, even as it appears from our small vantage point to be still and eternal. And you are part of it, a momentary presence within its arms, carried along by its rotation, made of materials that has been cycling through stars for billions of years. Let the arms of the galaxy hold you, as gently and as vast as the night sky. Let the bar stretch across the center of your thoughts and grow quiet and dim. Let sleep come like the drift between the arms, spacious and soft and full of stars. Let yourself be here, fully and without effort. Let your thoughts be soft. Let your body be soft. If there is any place where you're holding tension, a shoulder, a jaw, a hand, simply notice it and let it go. You do not need to hold anything right now. The night holds you. The darkness holds you. And in this chapter, we're going to talk about the spaces between the stars, the great invisible ocean that fills the Milky Way's disk, and from which all stars, including our own sun, were born. It is easy to think of the galaxy as being made of stars. When we look up at the night sky, the stars are what we see, those brilliant, individual points of light scattered across the darkness. And stars are certainly the most visible component of the Milky Way, the part that blazes with light and announces its presence across cosmic distances. But between the stars, filling the disk of the galaxy in vast, diffuse clouds and streams, is another component just as important to the galaxy's life: interstellar gas and dust. The disk of the Milky Way contains enormous quantities of this interstellar material. Gas, mostly hydrogen and helium, the simplest and most abundant elements in the universe, drifts through the disk in clouds of varying density, from the thin, diffuse gas that permeates the general interstellar medium to the much denser concentrations where conditions are right for stars to form. Woven through this gas are particles of dust, tiny grains of silicate and carbon compounds, ice-coated and dark, incredibly small individually, but collectively able to block starlight over large distances, creating those dark lanes and obscuring clouds that we see threading through the Milky Way band in the night sky. The interstellar medium, as astronomers call this mixture of gas and dust, is not static. It is in constant motion, stirred by the radiation and winds of massive stars, shocked and compressed by supernova explosions, swept up by the passage of spiral arms, and slowly, in certain places, drawn together by gravity into the denser structures that will eventually give birth to new stars. The interstellar medium is the raw material of the galaxy's ongoing creation, the substrate from which everything solid and luminous is slowly assembled. The densest and most important concentrations of interstellar material are called giant molecular clouds. These are enormous structures, truly enormous, some of them spanning hundreds of light years and containing enough mass to make tens of thousands of stars. Inside a giant molecular cloud, the gas has been compressed to densities far higher than the general interstellar medium, and the temperatures are very cold, typically only a few tens of degrees above absolute zero. In these cold, dark, dense interiors, molecules can form and survive. Hydrogen molecules, carbon monoxide, water ice, and dozens of other compounds that are the chemical precursors of planetary atmospheres, oceans, and living things. Giant molecular clouds are stellar nurseries. They are where the galaxy's next generation of stars is being born, right now, in slow motion processes that take millions of years to unfold. Within a giant molecular cloud, small regions of extra density can begin to collapse under their own gravity. As the gas falls inward, it heats up, spinning faster as it contracts, much as a spinning ice skater spins faster when she pulls her arms in. The collapsing core grows hotter and denser, and eventually, if enough mass has accumulated, temperatures at the center reach the extraordinary threshold of about 10 million degrees, at which point nuclear fusion ignites and a new star is born. The Milky Way forms approximately 1 to 2 solar masses worth of new stars every year. That is a relatively modest rate compared to some galaxies. There are starburst galaxies out there that form hundreds of solar masses of new stars every year, consuming their gas reserves in spectacular but short-lived bursts of creation. Our galaxy is more measured, more steady. It has maintained a relatively consistent rate of star formation over a long period, which is one of the reasons its disk shows such a wide range of stellar ages, from stars only a few million years old to stars billions of years old, all mixed together in the thin disk. Star formation is not equally efficient everywhere in the galaxy. It is more vigorous where the gas surface density is higher, where the raw material is more concentrated. The spiral arms, as we discussed in the previous chapter, are places of higher gas density, and accordingly they're where star formation is most active. When you see a bright nebula glowing in photographs of the Milky Way or other galaxies, those beautiful, luminous clouds of pink and red and blue, you are almost always looking at a star-forming region, a place where newly born massive stars are pouring ultraviolet radiation into the surrounding gas, causing it to glow with the light of excited hydrogen atoms. The Orion Nebula is perhaps the most famous star-forming region visible from Earth. Even to the naked eye, in the right conditions, it appears as a faint, fuzzy patch of light below the 3 stars of Orion's belt, a smudge of luminosity that reveals itself in binoculars as a complex, glowing cloud surrounding a cluster of young, hot stars. This nebula is a window into the ongoing process of star formation happening right now in our own cosmic neighborhood, only about 1,400 light-years away. The stars embedded within it are extraordinarily young by stellar standards, only a few million years old, still surrounded by the remnants of the cloud from which they formed. Beyond just producing new stars, the interstellar medium plays another crucial role in the galaxy's cycle of matter. When stars reach the end of their lives, they return a significant fraction of their mass back to the interstellar medium, through stellar winds, through planetary nebulae in the case of stars like our Sun, through the dramatic explosions of supernovae in the case of more massive stars. This return material is not the same as what was originally incorporated into the star. It has been processed by nuclear fusion in the star's interior, transformed from simple hydrogen and helium into heavier elements: carbon, oxygen, nitrogen, iron, silicon, and all the rest. When this enriched material mixes back into the interstellar medium, it raises the overall chemical complexity of the gas from which the next generation of stars will form. This is the galaxy's great cycle. Gas collapses into stars. Stars process the gas through nuclear fusion and then return it to space enriched with heavier elements. And the enriched gas collapses into the next generation of stars, which are consequently more chemically complex than their predecessors. Each generation of stars is born from slightly richer material than the last. Over billions of years, the interstellar medium has become progressively more enriched with the heavy elements that make up planets, rocks, water, and life. You are, in this very direct sense, the product of multiple generations of stellar chemistry. Your atoms were forged in stars that lived and died long before our sun was born, and the galaxy's ongoing cycle of creation is what made your existence possible. The central bulge of the Milky Way is different in this regard. The bulge currently shows little widespread active star formation, unlike the disk. The gas that once filled the bulge was consumed in an early, vigorous burst of star formation long ago. And today the bulge is dominated by old stars, stars that formed when the galaxy was young and that have been quietly burning ever since. The relative quiet of the bulge's star formation today is a contrast to the active, ongoing creation happening in the disk, and it reflects the different histories of these two components. As you lie in the dark and let these images drift through your mind, perhaps you can feel something of the galaxy's long, patient rhythm, the slow condensation of gas into stars, the millions of years of nuclear burning, the return of enriched material to space, the collapse again into new stars. It is a cycle without a clear beginning and without a clear end, just an ongoing transformation of matter from one form to another, across timescales so vast that any individual life, any individual star, is just a brief appearance in the middle of something much longer. The gas and dust of the interstellar medium are not empty space. They are the future. They hold within them the raw material of suns that have not yet been born, of worlds that have not yet formed, of chemical complexity that has not yet had a chance to arrange itself into something that can look up at the sky and wonder. All of that potential is out there right now, drifting in dark clouds, waiting for the slow gathering of gravity to begin its work. Let that thought rest gently with you. The galaxy is patient. It is always preparing for what comes next, always slowly organizing the raw materials of the future into the next generation of light. And right now, in this moment, you are resting in the middle of that patient, ancient process, made of star material, held by gravity, breathing air that was assembled from the same cosmic chemistry that fills the interstellar medium. The universe is working. You can rest. Settle in a little more. If you have been following along, you are perhaps already drifting, your thoughts growing softer at the edges, your awareness of the room around you gently fading. That is exactly where you want to be. Let the words come to you from a distance, like the sound of a quiet radio playing in another room, present and meaningful, but not demanding. We're going to talk about the chemistry of the stars, the elements that fill them, the history written in their compositions, the way that the Milky Way has slowly, over billions of years, enriched itself with the materials of complexity. Every star in the Milky Way is not exactly like every other. They differ in size, in temperature, in brightness, in age, but they also differ in something subtler and more revealing: their chemical composition. The proportions of elements present in a star's outer layers, the ratios of hydrogen to helium, of iron to oxygen, of carbon to silicon, carry information about when and where that star formed, about the history of the gas cloud from which it condensed, and about the long story of the galaxy's own chemical evolution. Reading the chemistry of stars is one of the most powerful ways astronomers have of understanding the Milky Way's past. The most fundamental chemical distinction among the Milky Way stars is their metallicity. In astronomy, the word metal has a different meaning than in everyday life. To an astronomer, any element heavier than hydrogen and helium is a metal, including carbon, oxygen, nitrogen, iron, silicon, and everything else on the periodic table beyond the two lightest elements. When astronomers talk about a star's metallicity, they are describing the proportion of these heavier elements in the star relative to hydrogen. A high metallicity star contains a relatively large fraction of heavy elements. A low metallicity star is composed almost entirely of hydrogen and helium, with very little else. And metallicity tells a story. In the early universe, shortly after the Big Bang, there were essentially no heavy elements at all. The universe consisted almost entirely of hydrogen and helium, with trace amounts of lithium. Every atom of carbon in your body, every atom of oxygen in the air you breathe, every atom of iron in your blood, none of these existed in the early universe. They were made later, inside stars, through nuclear fusion. As successive generations of stars formed, burned, and died, they scattered heavy elements into the interstellar medium, enriching each subsequent generation of star-forming gas with a slightly higher metallicity. The longer a region of the galaxy has been actively forming stars, the more metal-rich its gas, and therefore its stars, tend to be. This is why different regions of the Milky Way show different metallicities. The bulge, which formed early and vigorously, consumed a great deal of gas in rapid star formation long ago. That early, intense activity enriched the bulge's gas quickly, and as a result, bulge stars today are generally metal-rich. They contain a relatively high proportion of heavy elements compared to other parts of the galaxy. The bulge has had time for many stellar generations to cycle through, each one contributing to the chemical enrichment of the gas from which the next generation formed. The halo tells the opposite story. Halo stars are generally metal-poor. Some of them are among the most chemically primitive stars known, containing barely any heavy elements at all. Their composition's a whisper away from the pure hydrogen and helium of the Big Bang. These stars formed very early in the galaxy's history, when the interstellar medium had only just begun to be enriched by the first generation of massive stars. They are not just old, they are chemically ancient, carrying within their compositions the memory of a time when the universe was still in its infancy and the periodic table was still mostly blank. The disk of the galaxy sits between these extremes, but it is not uniform either. The thick disk and thin disk have different chemical signatures that reflect their different formation histories. Thick disk stars show what astronomers call enhanced alpha element abundances. They contain relatively high proportions of elements like oxygen, magnesium, neon, and calcium compared to their iron content. These alpha elements are produced in large quantities by the explosions of massive stars, supernovae, which happen quickly after a burst of star formation, enriching the gas with alpha elements on short time scales. Iron, by contrast, comes primarily from a different type of supernova that takes much longer to produce. The thick disk's chemical signature, high in alpha elements relative to iron, tells us that it formed during a period of rapid, intense star formation, when massive star deaths were delivering alpha elements to the interstellar medium faster than the slower, iron-producing supernovae could keep up. This matches the picture of the thick disk as a structure that formed early and quickly, in a burst of star formation during the first few billion years of the galaxy's life. The thin disk, which formed over a longer timescale, shows a different pattern. Its stars have had time to be enriched by both kinds of supernovae, and so their iron content has caught up with their alpha element content. Thin disk stars show a different balance of elements than thick disk stars, a balance that reflects the more gradual, sustained pace of star formation that has characterized the disk over most of the galaxy's history. By studying the chemical compositions of thousands of stars in different parts of the disk, astronomers can trace how the rate of star formation changed over time, how the interstellar medium evolved chemically, and how the different components of the galaxy assembled themselves. Age and metallicity are related, but not in a perfectly simple way. In general, older stars tend to be more metal-poor because they form from less enriched gas. But there are complications. Stars in the inner disk, closer to the galaxy's center where star formation has historically been more vigorous, tend to be more metal-rich at a given age than stars in the outer disk. This radial gradient in metallicity, the fact that the inner galaxy is more chemically enriched than the outer galaxy, is another piece of the galaxy's chemical story. It reflects the fact that star formation, and therefore chemical enrichment, has proceeded at different rates in different parts of the disk over the galaxy's history. What this all means, when you hold it together, is that every star in the Milky Way is a kind of time capsule. Its chemical composition records the state of the interstellar medium at the moment and place where it formed, the degree of enrichment, the history of star formation in its neighborhood, the balance of different types of stellar deaths that had contributed to the gas before it collapsed into the star. Astronomers who study stellar chemistry can reconstruct not just the history of individual stars, but the history of the galaxy itself. Its star formation rate over time, the sequence in which its different components formed, the ways in which different parts of the disk have evolved at different paces. There is something quietly profound about this. The chemistry of a star is not just a measurement. It is a biography. It tells where the star was born in the galaxy, when it was born, what the neighborhood was like when it formed, how many previous stellar generations had lived and died to create the conditions for its own existence. Stars do not speak, but they carry their histories written in the proportions of their elements, available to anyone patient enough to read them. And you are made of star chemistry too. The elements in your body are not random. They have histories. The carbon in your cells was fused in the cores of stars that died before the solar system formed. The oxygen in your lungs was scattered into space by stellar winds and supernovae. The iron in your blood was produced in the fiery deaths of massive stars. Your body is a mixture of chemical contributions from many different stellar generations, each generation slightly enriching the interstellar medium from which the next formed, in a slow accumulation that eventually produced the gas cloud that collapsed into our sun and the raw material for the Earth and everything on it. You are the product of the Milky Way's chemical evolution. You carry within you the record of its history in the proportions of your own elements. When astronomers measure the metallicity of the sun, which is relatively high, reflecting the fact that it formed late in the galaxy's history from well-enriched gas, they are reading part of the same story that is written in your body. The galaxy's chemistry is your chemistry. You are not separate from this ancient, ongoing process. You are one of its products. Let that thought be peaceful rather than overwhelming. You are not small in the face of the galaxy's enormity. You are its current, most complex expression, the most intricate arrangement of its matter that we know of. Billions of years of stellar chemistry, of gas clouds and supernovae and interstellar enrichment, led to the conditions that made you possible. The galaxy did not intend this, of course, but happened. Here you are, made of stars, resting in the dark, listening to the story of the system that made you. Let the chemistry of the cosmos settle quietly into your body. Let the weight of the elements, ancient, star-forged, yours, hold you gently against the ground. You belong here. You are made of this place. Rest in it now. Breathe gently. There is no rush, no destination, nothing to arrive at or complete. We are simply drifting through the Milky Way together, one quiet chapter at a time. And tonight we're going to visit some of the most beautiful and ancient objects in the entire galaxy, the globular clusters. These extraordinary structures orbit the Milky Way in the halo above and below the disk, and they are so old, so dense, and so beautiful that studying them has changed our understanding of the universe itself. Settle in and let their story come to you softly. Imagine a sphere of stars, not just a few stars or a few thousand, but hundreds of thousands of stars, sometimes 1 million or more, all packed together into a space only 100 or 200 light years across. At the center of such a cluster, the density of stars is so extraordinary that the average distance between neighboring stars might be only a fraction of a light year, many times smaller than the roughly 4 light years that separate our sun from its nearest stellar neighbor. If you lived on a planet near the center of a globular cluster, your night sky would be breathtaking, a dense, luminous swarm of stars in every direction. The sky so full of suns that true darkness would never really fall. These are globular clusters, and the Milky Way hosts a significant population of them, currently estimated at around 150, though the true number may be somewhat higher once hidden clusters behind the galactic dust are counted. They orbit the Milky Way on long, looping paths that take them far out into the halo, thousands of light years above and below the galactic disk, and then sweep them back and toward the galactic center before carrying them outward again. From the perspective of the disk, globular clusters move like visitors from another realm, diving through the galactic plane, and retreating back into the halo in long, eccentric orbits that take hundreds of millions of years to complete. What makes globular clusters especially remarkable is their age. They contain some of the oldest stars in the entire Milky Way, and by extension, some of the oldest stars in the known universe. Many globular cluster stars are 12 to 13 billion years old, putting their formation in the first billion years of the universe's existence. They formed before the galactic disk existed. They formed before most of the Milky Way's current structure had assembled itself. In a very real sense, globular clusters are older than the galaxy as we know it. Ancient structures that were already in place when the young Milky Way was still taking shape. This extreme age is one of the most useful things about globular clusters from an astronomical perspective. Because their stars are so old and were formed at roughly the same time from the same cloud of gas, they provide astronomers with some of the most precise natural clocks available for measuring cosmic time. By studying the mix of stars in a globular cluster, particularly by identifying the point at which the most massive surviving stars are leaving the main sequence and evolving into red giants, astronomers can estimate the cluster's age with considerable precision. This technique, applied to dozens of globular clusters, has helped establish the minimum age of the universe itself, confirming that the cosmos must be at least as old as the oldest globular clusters it contains. The chemical composition of globular cluster stars is, predictably, metal-poor. These are ancient stars, formed when the interstellar medium was only lightly enriched by the first generations of stellar deaths. Their low metallicity is a direct record of the early universe's chemical simplicity, a time before the long cycles of stellar birth and death had had enough time to significantly enrich the cosmic gas supply. When astronomers measure the metallicity of a globular cluster, they are reading a chemical timestamp, a record of how much heavy element enrichment had occurred by the time that cluster stars were born. Interestingly, globular clusters are not all the same age or the same metallicity. Some are more metal-rich than others, and this has led to an important insight about their origins. The more metal-rich clusters tend to orbit closer to the galactic center, while the more metal-poor clusters are distributed more widely throughout the halo. This pattern suggests that the metal-rich clusters formed in the denser, more rapidly enriched inner regions of the early galaxy, while the metal-poor clusters formed farther out, or in some cases, may have been captured from smaller galaxies that fell into the Milky Way long ago. This brings us to one of the most exciting aspects of globular cluster research: the connection between clusters and galactic mergers. Astronomers now believe that some of the Milky Way's globular clusters did not originally form within our galaxy at all. Instead, they were once associated with smaller dwarf galaxies that were captured and absorbed by the Milky Way over billions of years. When a dwarf galaxy is consumed by a larger galaxy, its stars are scattered into the halo as streams and shells. But its globular clusters, being so dense and compact, can survive the disruption and continue to orbit as distinct objects, carrying their foreign origin like a kind of cosmic passport. Identifying which globular clusters are native to the Milky Way and which were captured from infalling satellites is an active and exciting field of research. Some clusters show chemical signatures or orbital properties that are distinctly different from the majority, hinting at an origin in a different galaxy. The most famous example may be Omega Centauri, the largest and most massive globular cluster associated with the Milky Way, which many astronomers believe is not a true globular cluster at all, but the stripped-down remnant core of a small galaxy that was consumed by the Milky Way long ago. Its unusual size, its complex stellar populations, and its internal chemical variations all point to an origin more complex than a typical cluster. Some globular clusters show evidence of net rotation, the entire cluster turning slowly as a unit, rather than just the random orbital motions of individual stars within a gravitationally bound sphere. This rotation carries information about the cluster's formation and history, about the angular momentum of the gas cloud from which it formed, and the subsequent dynamics of its evolution. Clusters that were once part of satellite galaxies may show rotational signatures related to the orbital dynamics of their original host. Globular clusters are not static either. Over billions of years, gravitational interactions within the cluster, individual stars passing close to each other and exchanging energy, cause the cluster to slowly evolve. Lighter stars tend to gain energy and drift toward the cluster's outer regions, while heavier stars and stellar remnants sink toward the center in a process called mass segregation. In old clusters, this process has had billions of years to operate, concentrating the densest stars, neutron stars, white dwarfs, possibly black holes, toward the cluster's core, while the less massive stars occupy the outer regions. Occasionally, close encounters between stars and the dense core of a globular cluster can produce exotic objects called blue straggler stars, stars that appear younger and hotter than they should be given the cluster's age. These rejuvenated stars likely result from collisions or mass transfers between close stellar pairs, in which one star gains material from another and appears to start a new phase of life. In the crowded centers of globular clusters, where stars pass much closer to each other than they ever do in the general galactic field, these unusual encounters are far more common than in the disk around us. Looking up at a globular cluster through a telescope, even a small one, is one of the most quietly spectacular experiences in amateur astronomy. What appears to the naked eye as a faint, fuzzy patch of light resolves in a telescope into a luminous sphere of innumerable stars, dense at the center and gradually thinning toward the edges, like a handful of salt thrown gently into a dark room and caught suspended in a gentle glow. Some of the most famous globular clusters, Omega Centauri, 47 Tucani, M13 and Hercules, are visible to the naked eye from dark sites, pale smudges that look like misplaced fragments of the Milky Way, suspended in the halo above and below the galactic plane. These ancient spheres of stars are among the most enduring structures in the Milky Way. They have survived for nearly the entire age of the universe. They have watched the galaxy grow and change around them, absorbed the light of generations of stars, and continued in their long orbits through the halo, patient and persistent. They are, in a sense, the galaxy's oldest witnesses, structures that remember a time before the spiral arms existed, before the sun was born, before the earth was formed. As you drift towards sleep, let the image of a globular cluster settle into your imagination. A soft sphere of ancient light, dense at the heart and fading gently toward its edges, turning slowly in the dark halo of the galaxy. Hundreds of thousands of stars, each one older than the Earth, each one quietly burning in the long night of the cosmos. They have been here for nearly the entire life of the universe, and they will be here long after tonight, long after all our small human stories have been told. Old light, patient light, enduring, ancient, beautiful. Let be the last image in your mind as your thoughts grow slower and the night deepens around you. Rest well. Let your body be completely still now. Let your thoughts be completely soft. We are going to the center of the galaxy, the most extreme, the most dramatic, the most extraordinary place within our entire galactic home. This is the heart of the Milky Way, a place hidden from our direct view by thousands of light years of dust and gas, and yet known to us through the patient, ingenious work of generations of astronomers. Settle in, breathe slowly, and let us approach it together, gently, from a safe distance of 26,000 light years. When you look toward the constellation Sagittarius in the summer sky, that rich, complex patch of the Milky Way low in the southern sky from the northern hemisphere, bright and layered and full of depth, you are looking in the direction of the galactic center, not at the center itself, because the dust and gas between us and the core block our direct optical view completely. But in that direction, if you imagine a line drawn from your eyes through the heart of the Milky Way band in Sagittarius, continuing through the plane of the galaxy, it would eventually reach the galactic center, 26,000 light-years away, hidden behind curtains of dust. The heart of our galaxy lies waiting. At that center, there is something that took decades of patient observation to confirm, and whose existence had been suspected long before it was proven: a supermassive black hole. Its name is Sagittarius A star, written in scientific notation as Sagittarius A*, and pronounced Sagittarius A star. It is a compact radio source, meaning it emits radio waves that telescopes can detect even through the dust that blocks visible light. And for decades after its discovery in the 1970s, astronomers debated its true nature. Was it truly a black hole? And if so, how massive? The answer came from one of the most remarkable observational campaigns in the history of astronomy. Beginning in the 1990s and continuing for more than 2 decades, astronomers used infrared telescopes to peer through the dust toward the galactic center and track the motions of individual stars in the very heart of the Milky Way. What they found was extraordinary. Stars near the galactic center were moving at tremendous speeds, following tight orbits around a point that appeared to emit no light of its own. By measuring the speeds and orbital periods of these stars, using the same principles by which planets' orbits reveal the mass of the Sun, astronomers could calculate the mass of whatever object was exerting such powerful gravitational influence. The result was unambiguous. The object at the galactic center has a mass of more than 4 million times the mass of our Sun. 4 million solar masses, contained within a region smaller than our solar system. The only known class of object that can pack that much mass into that smallest space is a black hole. Specifically, a supermassive black hole, the largest variety of these extraordinary objects that astronomers have identified. In 2020, the astronomers who led this work, Reinhard Genzel and Andrea Ghez, shared the Nobel Prize in Physics for the discovery, a recognition of the decades of careful, patient work that had gone into confirming the nature of our galaxy's central engine. A black hole is a region of space where gravity has become so extreme that nothing, not matter, not light, not any signal of any kind, can escape from within a certain boundary called the event horizon. Anything that crosses the event horizon is, from the perspective of the outside universe, gone forever. For Sagittarius A*, the event horizon is relatively small given the black hole's mass. If you scaled our solar system, the event horizon of Sagittarius A* would fit within the orbit of Mercury. But the gravitational influence of this mass extends far beyond the event horizon, shaping the motions of stars and gas across a large region of the galactic center. Near Sagittarius A*, the environment is extreme in ways that are difficult to fully imagine. The density of stars in the innermost few light years around the black hole is extraordinary. Thousands of stars in a volume that would contain only our solar system and its nearest neighbors in the less crowded reaches of the galactic disk. Gas falling inward from the surrounding region forms a rotating disk or ring structure that extends several light years out from the black hole. As this gas spirals inward, it can heat up and emit radiation, and when enough material falls onto the black hole at once, it can produce brief flares of energy visible across many wavelengths. The galactic center is not currently in an active, highly energetic state. Sagittarius A* is, by the standards of supermassive black holes and other galaxies, relatively quiet, what astronomers call quiescent. It is not currently consuming large amounts of gas in a sustained, powerful way, and it does not produce the brilliant jets of energy that we see from actively feeding black holes in distant galaxies. But it has not always been so quiet. Evidence suggests that millions of years ago, the black hole at our galaxy's center went through periods of much higher activity, producing powerful outflows that shaped the surrounding environment. The echoes of this past activity are still being studied and debated. The black hole is not alone at the center. The innermost region of the galaxy, within a few light years of Sagittarius A*, contains a dense cluster of stars, some of them young, massive, and hot, which is somewhat surprising given how difficult it should be for star formation to occur in the extreme gravitational environment near a supermassive black hole. How these young stars formed so close to the black hole is a puzzle that astronomers call the paradox of youth, and it remains an active area of research. Some ideas involve star formation in a dense disk of gas around the black hole, where conditions might be extreme enough to trigger collapse in ways different from ordinary star formation in the disk. The stellar motions near the galactic center are unlike anything in our local neighborhood. Stars whip around Sagittarius A* at tremendous speeds. Some of the innermost known stars complete their orbits in only a few years, reaching velocities of thousands of kilometers per second at their closest approaches to the black hole. Observing these stellar orbits over years and decades has been one of the primary ways of measuring the black hole's mass and position, and the quality of these measurements has improved dramatically with advances in telescope technology, including the use of adaptive optic systems that correct for the blurring effects of Earth's atmosphere. The central bar and bulge of the galaxy feed into this extreme environment in complex ways. The bar, as we discussed earlier, channels gas from the outer disk toward the inner regions of the galaxy. Some of this gas eventually flows all the way to the central few hundred light years, where it can be caught up in the gravitational influence of the central mass concentration and gradually spiral inward towards Sagittarius A star. This slow, irregular inflow is one of the ways the black hole sustains itself over time, growing gradually larger as it accretes matter from its galactic environment. There is a beautiful irony in the fact that the very center of our galaxy, the gravitational anchor around which the entire system turns, the most massive concentration of matter within 100,000 light years, is something we cannot see with our own eyes. The dust that fills the galactic disk, the very material that represents the galaxy's ongoing creative activity, is what hides the galaxy's most extreme feature from us. We must use other tools, infrared telescopes, radio observatories, X-ray satellites, to penetrate the dust and observe the center indirectly. The center of our home is hidden from us, accessible only through the patience of science and the ingenuity of instruments. And perhaps there is something fitting in that. The heart of things is often the hardest to see directly. It must be approached carefully, through indirect means, through patient accumulation of evidence and understanding. The galactic center is not available for casual inspection. It rewards only those who are willing to look in new ways, to use instruments that perceive wavelengths of light beyond what human eyes can detect, to track the subtle motions of stars over years and decades. The center yields its secrets slowly to the patient. As you lie here in the dark, far from the center, 26,000 light years away, on a small planet orbiting a modest star in a quiet spur of a spiral arm, perhaps you can feel the faint, impossible to perceive tug of that distant mass. You cannot feel it, of course. The gravitational influence of Sagittarius A* on you personally is utterly negligible, dwarfed by the gravity of the Earth beneath you. But you are, in some sense, in orbit around it. Everything in the Milky Way is ultimately orbiting the galactic center. Your 26,000 light-year distant orbit, completed once every 200 million years, is as real as the orbits of the stars that whip around Sagittarius A* in just a few years. We are all circling the center. All of us. Every star in the sky, every planet, every cloud of gas and dust, moving in vast, slow, coordinated motion around the black heart of our galaxy. It is quiet and it is distant, and it is hidden behind curtains of dust. But it is there, anchoring everything, the still point around which the whole great wheel of the Milky Way turns. Rest now in this slow orbit, in this quiet dark. The center holds. Everything is in motion, and everything is held. You can stop trying to hold yourself up. The galaxy has been doing that, in its own way, for billions of years. Stay with me a little longer. We have traveled through the visible Milky Way, its stars and arms, its dust and gas, its ancient clusters, and its extraordinary center. But now we're going to turn our attention to something invisible, something that cannot be seen, that does not emit light, that does not reflect light, that passes through ordinary matter without any apparent interaction, and yet which may constitute most of the mass of the Milky Way. We're going to talk about dark matter, one of the deepest and most beautiful mysteries in all of modern science. The story of dark matter begins with a puzzle about motion. As astronomers mapped the rotation of the Milky Way, measuring how fast stars and gas clouds at different distances from the galactic center orbit around it, they expected to find a particular pattern. In any rotating system where most of the mass is concentrated near the center, the objects farther from the center should orbit more slowly, just as the outer planets of our solar system orbit the sun more slowly than the inner ones. Jupiter takes 12 years to complete one orbit around the sun. Mercury takes only 88 days. The farther you are from the central mass, the slower you move in your orbit, because gravity weakens with distance. In the Milky Way, astronomers expected to find the same pattern. Stars near the galactic center, embedded in the dense bulge, should orbit fastest. Stars farther out in the disk, at our sun's distance and beyond, should orbit progressively more slowly. The galaxy's rotation curve, a graph showing orbital speed versus distance from the center, should, by this reasoning, rise from the center and then fall off, like the curve of a bell, as you move outward. But that is not what they found. Instead, the rotation curve of the Milky Way, and of virtually every other spiral galaxy that has been carefully measured, remains surprisingly flat. Stars at large distances from the center orbit at roughly the same speed as stars much closer in, instead of slowing down as you move outward through the galaxy. As gravity predicts they should if most of the mass is concentrated near the center, the orbital speed staying nearly constant far out into the disk, and even beyond it. This is deeply puzzling. If stars far from the galactic center are moving faster than they should given the visible mass of the galaxy, something must be providing additional gravitational force to keep them in their orbits. Either the laws of gravity, as we understand them, work differently on galactic scales, which some researchers have explored with limited success, or there is additional mass in the galaxy that we cannot see, mass that does not emit light, does not absorb light, does not interact electromagnetically in any way that makes it detectable through conventional astronomical observation. Mass that reveals its presence only through its gravitational influence on the things we can see. This unseen mass is what astronomers call dark matter. And the Milky Way, like virtually every other galaxy that has been carefully studied, appears to be embedded in an enormous halo of it. The dark matter halo of the Milky Way is far larger than the visible galaxy. It extends far beyond the stellar disk and the stellar halo, reaching out to distances of several 100,000 light years or more in every direction. And it is far more massive than the visible components of the galaxy. The total mass of dark matter in the Milky Way's halo is estimated to be many times greater than the total mass of all the stars, gas, and dust put together. The visible galaxy that we can observe, all its stars and gas and dust, is like the small, luminous tip of a vast, dark iceberg. The phrase dark matter is somewhat misleading. It is not dark in the way that a dark room is dark, the absence of light. It is dark in the sense of being invisible, undetectable by any currently available means of observation other than its gravitational effects. We know it is there because of what it does to the things around it. We know it is real because without it, the observed motions of stars and gas and galaxies, and the motions of galaxies themselves within galaxy clusters, make no sense under our current understanding of gravity. Whatever dark matter is, it is not nothing. What dark matter actually is remains one of the most important open questions in physics. The leading candidates are exotic subatomic particles that interact with ordinary matter only through gravity and possibly the weak nuclear force. Particles so elusive that they could pass through the entire Earth without leaving any detectable trace. Despite decades of searching, with detectors placed deep underground to shield them from the constant rain of cosmic rays, with particle accelerators trying to produce dark matter particles directly, with satellite observatories looking for indirect signals from dark matter annihilation in space. No dark matter particle has yet been definitively detected and identified. It is one of the most frustrating and fascinating problems in modern science. The motions of the Milky Way's satellite galaxies, the small galaxies that orbit our galaxy, which we will explore in the next chapter, also trace the shape and extent of the dark matter halo. Because the satellites orbit within the dark matter halo, their velocities and distributions reflect the halo's mass and geometry. Studies of satellite galaxy orbits have helped constrain not just the total mass of the halo, but its shape, whether it is perfectly spherical or somewhat flattened or tilted relative to the disk. Intriguingly, some evidence suggests that the Milky Way's dark matter halo may be tilted at an angle relative to the plane of the galactic disk. If true, this could help explain the disk's warp, the phenomenon we discussed in an earlier chapter, where the outer edges of the galactic disk curve above and below the midplane. A tilted dark matter halo would exert a gravitational influence that is not perfectly aligned with the disk's rotation, and this misalignment could generate or sustain the disk's warp over time. The invisible dark matter halo in this picture is literally bending the visible galaxy through its gravitational influence. There is something profoundly humbling about dark matter. For centuries, astronomy has been the science of light, of observing what luminous objects emit and absorb and scatter, of reading the messages carried by photons across cosmic distances. And light has taught us an extraordinary amount about the universe. But dark matter is a reminder that the universe contains at least one major component that is entirely opaque to our most fundamental observational tool. The vast majority of the Milky Way's mass is invisible to us, detectable only as a gravitational ghost shaping the motions of everything we can see. We live inside a galaxy that is mostly dark. The stars and gas and dust that we have been exploring throughout this journey, all of that luminous, visible, comprehensible material, is a minority component embedded within and shaped by a far larger invisible structure that we do not understand and cannot directly observe. The visible Milky Way is, in this sense, like the face of a person whose inner life is largely hidden from view, known only through the effects it has on behavior, detectable only through careful, patient inference. And yet the dark matter is there. It holds a galaxy together. Without it, the outer stars of the Milky Way would fly free into intergalactic space. The disk would disperse. The whole beautiful structure we have been exploring would dissolve. Dark matter is what makes the galaxy possible. It is the invisible architecture upon which all the visible splendor is hung. Every star we see, every nebula, every spiral arm, every ancient globular cluster, all of it exists within the gravitational embrace of something we cannot see but cannot do without. There's a kind of poetry in this. The most important structural component of our galaxy is the one we cannot observe directly. The foundation of everything is invisible. The greatest mass is the darkest. In trying to understand the Milky Way, we find ourselves confronting not just what we know, but the boundaries of what we can know, the edges of our observational reach, where the universe keeps its deepest secrets. Let that mystery be restful rather than troubling. Not every question needs an answer tonight. The dark matter halo surrounds you, as it has always surrounded you, vast and silent and invisible, holding the galaxy together with patient, enormous gravity. You are inside something mostly invisible, mostly unknown, and entirely stable. The dark matter has been here for as long as the galaxy has, and it will continue to hold everything together long after tonight. Rest inside the invisible embrace of the cosmos. Let the mystery of dark matter be a kind of comfort, a reminder that the universe is larger and stranger and more full than anything we can fully comprehend, and that this is not frightening. It is simply vast, and in its vastness, there is more than enough room to rest. Let your breathing be very slow now. Let your body be very heavy. We're going to spend this chapter thinking about motion. The motion of the galaxy itself, the endless turning and flowing of stars and gas through the vast disk and halo of the Milky Way. There is something deeply relaxing about contemplating motion on this scale, because it is so enormous and so slow that it feels, from where we are, like perfect stillness. The galaxy is in constant motion, and yet it appears eternally still. Just like you, right now, breathing, the quiet motion of your chest rising and falling, otherwise resting and at peace. The Milky Way rotates. This is one of its most fundamental properties, the organizing principle of the disk structure, and the reason the disk exists at all in its flat, wide form. Billions of stars, tracing their individual orbits around the galactic center, collectively produce the impression of a rotating disk, a great wheel of stars turning in the dark of space. Not all at the same speed, not all in perfect lockstep, but on average in the same direction, in the same broad plane, all participating in the same great slow turning. Most stars in the disk orbit in the same direction, the direction we call prograde rotation, which is the direction of the galaxy's overall spin. When you look at the Milky Way from above the North Galactic Pole, the disk rotates counterclockwise, and most disk stars orbit in this direction. This coherent rotation is one of the clearest signatures of the disk's formation from a single, large, rotating gas cloud that collapsed and flattened into the disk as it spun. The rotation is a memory of the galaxy's formation, preserved in the orbits of hundreds of billions of stars. But not all parts of the Milky Way rotate at the same rate, or in the same organized way. The thick disk, as we mentioned in an earlier chapter, rotates more slowly than the thin disk. Its stars have, on average, less angular momentum, a reflection of the different formation history and the different population of stars it contains. Thick disk stars tend to have orbits that are more eccentric and more inclined to the galactic plane than thin disk stars, giving the thick disk a somewhat puffier, less ordered character than the thin disk's more precisely organized rotation. The halo is different still. Halo stars do not share the disk's organized rotation. Instead, they orbit at many different angles, some in prograde orbits like the disk, some in retrograde orbits moving in the opposite direction, some in orbits that carry them steeply above and below the plane, looping far into the halo before swinging back through the disk region. This chaotic, multi-directional distribution of halo star orbits is a key piece of evidence for how the halo formed. Not from the same orderly collapsing disk as the thin disk, but assembled over time from the debris of smaller galaxies and protogalactic fragments that fell into the growing Milky Way from many different directions. Many halo stars are classified as high-velocity stars, not because they are inherently moving at extraordinary speeds relative to the galactic center, but because their orbital orientations differ so dramatically from the Sun's nearly circular, prograde orbit that they appear to move very fast relative to us. When astronomers measure the velocity of a halo star from Earth, they subtract the Sun's own motion through the galaxy. If a halo star happens to be moving in the opposite direction, in retrograde orbit, its velocity relative to the Sun is the sum of both orbital speeds, which can be enormous. These apparently high-velocity stars are windows into the halo's chaotic orbital structure. The disk is not a perfectly smooth and stable structure. It is dynamically active, meaning it responds to perturbations, to the gravitational influences of passing objects and internal instabilities, in ongoing and sometimes dramatic ways. The warp of the outer disk that we discussed in an earlier chapter is one example of the disk's dynamic responsiveness. The disk is not rigid. It flexes and responds to the gravitational environment around it, and this responsiveness produces features like the warp, which may be driven by the gravitational influence of the Milky Way's satellite galaxies or its dark matter halo. The galaxy also wobbles. Precise measurements of stellar positions and motions have revealed that the galactic disk has a kind of wobble or breathing motion. Oscillations in the positions of stars above and below the midplane, waves propagating through the disk, subtle perturbations that suggest the disk has been disturbed by outside influences not too long ago in astronomical terms. The most likely culprit is the Sagittarius dwarf galaxy, a small satellite galaxy that has been orbiting the Milky Way and repeatedly plunging through its disk over the past billion or so years. Each passage sending ripples through the disk structure the way a stone dropped into a pond sends ripples across the water surface. Stellar streams are another signature of the galaxy's dynamic past. When a globular cluster or a small satellite galaxy comes too close to the Milky Way's gravitational center, tidal forces, the difference in gravitational pull between the near side and the far side of the object, can stretch and shred it, pulling its stars out into long, curving streams that trace the object's past orbital path around the galaxy. These stellar streams can persist for billions of years, gradually spreading around the galaxy in faint ribbons of stars. By mapping these streams, their positions, their velocities, and their chemical compositions, astronomers can reconstruct the past orbits of the objects that produce them, effectively reading the history of galactic mergers and tidal disruptions from the debris left behind. The most prominent example is the Sagittarius stream, the trail of stars left by the Sagittarius dwarf galaxy, as it has been gradually consumed by the Milky Way over the past few billion years. This stream wraps entirely around our galaxy in great arcs, sometimes above the disk and sometimes below it, containing stars from the Sagittarius galaxy that have been tidally stripped away over multiple orbital passages. By studying the Sagittarius stream in detail, astronomers have learned not just about the Sagittarius galaxy itself, but about the shape and mass of the Milky Way's dark matter halo, which controls the stream's shape through its gravitational influence. The galaxy, in short, is not settled. It is not a finished object sitting perfectly still in its final configuration. It is an ongoing process, a dynamic system responding to its own internal instabilities and to the continuing gravitational interactions with the other galaxies and structures in its environment. It has been disturbed in the past and will be disturbed again. It has consumed smaller galaxies and will consume more. It is growing, evolving, slowly changing in ways that unfold over timescales so vast that from a human perspective they appear completely static. This dynamism is invisible to us in our daily lives. The sky looks the same tonight as it did 1,000 years ago, and as it will look 1,000 years from now. The stars appear fixed and unchanging, the constellations stable, the Milky Way a permanent band of soft light across the sky. But beneath this apparent permanence, everything is in motion. Stars are drifting, slowly changing their positions relative to each other over millions of years. Streams of tidally disrupted stars are wrapping around the galaxy in arcs that take hundreds of millions of years to complete. The disk is wobbling in response to ancient gravitational disturbances. The halo stars are looping through their eccentric orbits. Everything is moving, everything is dynamic, And the stability we see is just the stillness of motion, so vast and slow that it exceeds the scope of our perception. There's a beautiful parallel here to the stillness of sleep. When you are deeply asleep, you are not motionless. Your heart beats, your lungs breathe, your blood flows, your brain processes the day's experiences, your body repairs and restores itself. All of this is motion. All of this is dynamic process. And yet from the outside, you appear still and at rest, serene and unchanging. The appearance of stillness is the surface of something much more active and alive underneath. The galaxy is like that. Its surface appearance, the fixed stars, the permanent constellations, the stable band of the Milky Way, is the surface of something much more active and alive, moving on timescales too vast for us to perceive directly. Beneath the apparent stillness, everything is turning, flowing, streaming, wobbling, responding. The galaxy is alive in the way that deep, peaceful sleep is alive, active at a level below our ordinary awareness, busy with processes too slow or too deep for the conscious mind to follow. You can let go of the need to keep track of all that motion. You do not need to follow it with your mind. It is happening whether you attend to it or not, and it will continue long after this night has passed. The galaxy turns, the streams flow, the disk wobbles, the halo stars loop through their long orbits. All of it continues, quiet and vast and patient, while you rest. The motion of the cosmos is the background of your sleep. Let it carry you. The night is very deep now. Let your awareness be soft and wide, like the halo of the galaxy itself, spread thinly over a large area, not concentrated on any one thing, just gently present. In this chapter, we're going to step back from the Milky Way itself and look at its companions, the smaller galaxies that orbit our own, the satellites and attendants that travel with us through the cosmos, each one a world of stars in its own right, each one telling a story about how the Milky Way has grown and changed over its long history. The Milky Way is not alone. It is surrounded by a retinue of smaller galaxies, dwarf galaxies and satellite systems of various sizes, that orbit our galaxy in long, looping paths drawn by its gravity, shaped by its tidal forces, slowly being incorporated into it over cosmic time. These satellite galaxies range from relatively large structures, containing hundreds of millions of stars, down to the smallest known dwarf galaxies with only a few thousand stars, barely more than an especially rich globular cluster, though distinguished by their dark matter content and their dispersed, gravitationally bound nature. The two most prominent companions of the Milky Way are the Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud. These are the Milky Way's largest satellite galaxies, and from the southern hemisphere of Earth, they are visible to the naked eye as two detached patches of the Milky Way, floating in the southern sky like fragments that have broken off from the main galactic band. They are not fragments, of course. They are independent galaxies in their own right, each one a sprawling system of stars, gas, and dust, orbiting the Milky Way at a distance of roughly 160,000 light-years for the large cloud and roughly 200,000 light-years for the small cloud. The Large Magellanic Cloud is particularly remarkable. It is classified as an irregular galaxy, not a clean spiral, not a smooth elliptical, but a somewhat chaotic, asymmetric structure with regions of intense star formation scattered through it. The Large Magellanic Cloud is currently forming stars at a vigorous rate, and it contains some of the most spectacular star-forming regions in the local group, the collection of galaxies that includes the Milky Way and its neighbors. The Tarantula Nebula, within the Large Magellanic Cloud, is one of the largest and most energetic star-forming regions known, so active that if it were as close to us as the Orion Nebula, it would cast shadows on Earth. The Magellanic Clouds are connected to the Milky Way not just gravitationally, but physically. There's a long stream of gas, called the Magellanic Stream, that trails behind the clouds in their orbit, stretching across a large fraction of the sky. This stream was pulled out of the clouds by tidal interactions with the Milky Way over millions of years, and it represents a continuous supply of raw material flowing from the clouds toward the Milky Way. Some of this gas is expected to eventually fall into the Milky Way's disk, providing fresh fuel for future star formation. Beyond the Magellanic Clouds, the Milky Way is attended by dozens of smaller satellite galaxies. Many of these are classified as dwarf spheroidal galaxies, small, roughly spherical, gas-poor systems containing mostly old stars and large amounts of dark matter relative to their visible stellar mass. They have names like Sculptor, Fornax, Carina, Sextans, and Leo, often named for the constellations in which they appear when viewed from Earth. They are faint and diffuse, spread over large areas of sky, but containing relatively few stars compared to the Milky Way. And discovering and cataloging them has been an ongoing project as telescopes have become sensitive enough to detect ever fainter systems. Some satellite galaxies are in the process of being tidally disrupted, pulled apart by the Milky Way's gravity. The Sagittarius dwarf galaxy, which we mentioned in the previous chapter, is the most dramatic example currently known. This small galaxy has been orbiting the Milky Way for billions of years, passing through the galactic disk on each orbit, and each passage has stripped away more of its stars, stretching them into the long Sagittarius stream that wraps around the galaxy in great arcs. What remains of the Sagittarius dwarf's core is still identifiable as a distinct concentration of stars, but much of its original stellar population has been scattered into the stream, incorporated into the Milky Way's halo. The Sagittarius example is not unique. The Milky Way has consumed many satellite galaxies over its history, and the halo is full of the debris of these past mergers, stellar streams from long-disrupted satellites, substructures in the halo that trace the orbital paths of accreted galaxies, chemical anomalies that mark clusters and stars imported from elsewhere. The Milky Way has been, in a real sense, a cannibal, growing partly by consuming smaller neighbors, incorporating their stars and gas and dark matter into its own structure. This accretion is not a violent or sudden process. It unfolds over billions of years as the satellite galaxy makes multiple orbits around the Milky Way, each orbit slightly altered by tidal forces and the gravitational influence of the disk, gradually losing stars to the tidal stream, gradually dissolving from a distinct galaxy into a diffuse cloud of stars that eventually blends into the halo. From the perspective of a star within a disrupting satellite galaxy, the experience, if a star could experience anything, would be an extremely gradual awareness of increasing isolation as neighboring stars drift away over millions of years and the satellite's coherence slowly dissolves. The accretion of satellite galaxies continues today. The Magellanic Clouds are not on a stable, permanent orbit around the Milky Way. They are likely on their first or second close approach, falling toward the Milky Way under its gravitational influence, and eventually, on timescales of billions of years, they too will be disrupted and absorbed. The Milky Way will consume its largest current satellites, incorporating their stars and gas into its own structure and growing slightly larger in the process. Mapping the satellite galaxies and their tidal streams is one of the most powerful tools astronomers have for understanding the shape and mass of the Milky Way's dark matter halo. The streams trace the gravitational potential of the galaxy, the shape of the invisible dark matter structure through which they have flowed. By comparing the observed positions and velocities of stream stars with theoretical models of how a stream should behave in a given gravitational field, astronomers can constrain the dark matter halo's mass, extent, and geometry. The satellites and their streams are, in effect, test particles that map the invisible architecture of our galaxy. Some of the Milky Way's satellite galaxies may themselves have satellites, small dwarf galaxies orbiting a somewhat larger dwarf galaxy, which is in turn orbiting the Milky Way. This kind of hierarchical structure, galaxies within galaxies, each level orbiting the next, is a prediction of our current models of how structure forms in the universe under the influence of dark matter. The universe assembles its large structures from smaller ones, galaxies from dwarf galaxies, clusters from individual galaxies, all held together by the pervasive influence of dark matter on every scale. Looking up at the night sky from the southern hemisphere and seeing the Magellanic Clouds, those two pale, cloud-like patches floating separately from the main band of the Milky Way, is one of the most quietly moving experiences in astronomy. You are looking at two entire galaxies, each containing hundreds of millions of stars, each a world of almost incomprehensible size, and they appear to the naked eye as little smudges of light, no larger than the tip of your thumb held at arm's length. The scale is vertiginous in the most peaceful way, the feeling of enormous distance and enormous size compressed into a tiny, gentle glow. Our galaxy has companions. It is not alone in space, not isolated in the dark, not drifting solitary through an empty universe. It travels with its retinue of satellites, gravitationally bound to them, slowly consuming some while others continue their long orbits, all of them part of the same extended gravitational family. And beyond the satellites, there are other galaxies, other major members of the local group, including the Great Spiral of Andromeda, that we will meet in the next chapter. For now, let the image of the satellite galaxies settle gently into your mind. Small galaxies accompanying a large one through the cosmos. Stars that have been captured from other systems, now orbiting in long streams through the halo. The Milky Way growing slowly, patient and gravitationally powerful, absorbing the smaller systems that come within its reach. We are part of something that has always been gathering, always growing, always expanding its embrace. Rest inside that gathering. Let the galaxy hold everything together, including you, quietly, on this small world, in this deep night. We're going to step back even further now, farther than we have gone in any previous chapter. We have explored the Milky Way in detail, its structure, its stars, its center, its satellites, its invisible dark matter. But now we're going to zoom out, the way a camera pulls back from a close portrait to reveal the wider landscape, and look at our galaxy from the outside, at its place within its cosmic neighborhood, its membership in a larger community of galaxies, and ultimately its position within the vast architecture of the universe itself. Breathe slowly. Let your mind expand outward, gently, without strain. The Milky Way is a member of what astronomers call the local group, a collection of galaxies that are gravitationally bound to each other, traveling through the universe together, held in mutual orbit by their combined mass. The local group is our immediate cosmic neighborhood, the collection of galaxies that are close enough to the Milky Way that their gravitational influence is significant, that their light reaches us in recognizable detail rather than as distant, unresolved points. The local group contains several dozen known members, but it is dominated by two large spiral galaxies, the Milky Way and the Andromeda Galaxy, also known by its catalog designation Messier 31, or simply M31. These two great spirals are the heavyweights of the local group, far more massive than any of the other members, and it is their mutual gravitational influence that largely defines the dynamics of the group as a whole. Between them, they account for the vast majority of the local group's visible stellar mass. Andromeda is remarkable in its own right. It is the largest spiral galaxy in the local group, somewhat more massive than the Milky Way, containing perhaps 1 trillion stars, more than the Milky Way's several hundred billion. It lies at a distance of approximately 2.5 million light-years, which makes it the most distant object visible to the naked eye under good conditions. On a dark night, far from city lights, you can see Andromeda as a faint, elongated smudge in the constellation of the same name, a tiny, pale ellipse of light that your eye might mistake for a cloud. That faint smudge is an entire galaxy, 2.5 million light-years away, containing 1 trillion stars. The light you see when you look at Andromeda tonight left that galaxy 2.5 million years ago. It has been traveling through space at the speed of light ever since, crossing the intergalactic void between two great galaxies, arriving at your eye as a faint smudge of pale light on a clear night. When that light departed Andromeda, our ancestors were not yet quite human. The stone tools of early Homo were just beginning to appear in Africa. The world was in an ice age, and the light from Andromeda was already on its way. The third significant member of the local group is the Triangulum Galaxy, also called M33, a somewhat smaller spiral located about 3 million light-years away. It is fainter and less prominent than either the Milky Way or Andromeda, but it is still a substantial galaxy in its own right, containing several tens of billions of stars and hosting its own active regions of star formation. Under exceptional observing conditions from a truly dark site, Triangulum is visible to the naked eye, though it requires very dark skies and patience. The rest of the local group is composed of dwarf galaxies, small, satellite-like systems orbiting the dominant spirals. Most of them are faint, irregular or ellipsoidal in shape, gas-poor and dominated by old stars or dark matter. Some orbit the Milky Way, as we discussed in the previous chapter. Others orbit Andromeda. A few may be relatively independent members of the group, not strongly associated with either of the two dominant spirals. New members of the local group continue to be discovered as telescopes become sensitive enough to detect ever fainter and more diffuse systems. The local group itself is not an island in the universe. It is embedded in a much larger structure called the Virgo supercluster, a vast collection of galaxy groups and clusters spanning roughly 100 million light-years, of which the local group is just one small component near the outskirts. The Virgo supercluster is centered on the Virgo cluster, a rich concentration of more than 1,000 galaxies about 50 million light-years away, whose gravitational pull has a measurable, if subtle, influence on the motions of galaxies throughout the surrounding region, including our own local group. Even a Virgo supercluster is not the largest structure we inhabit. More recent analyses of galaxy surveys have identified an even grander structure called Laniakea, a supercluster of superclusters spanning roughly 500 million light-years, of which the Virgo supercluster is just one component. Laniakea contains roughly 100,000 galaxies and has a total mass about 100 million billion times the mass of the Sun. The Milky Way, with its 100+ billion stars, sits somewhere in the outer reaches of this enormous structure, one small galaxy among a vast cosmic web. The word Laniakea comes from the Hawaiian language and means immeasurable heaven or open skies, a name chosen by the astronomers who identified and mapped this structure, a name that reaches for the same quality of awe that every culture has felt when confronting the enormity of the sky. Immeasurable heaven, a fitting name for a structure of 500 million light-years across, containing 100,000 galaxies, with the Milky Way as one nearly invisible member. But even on these vast scales, the Milky Way and its local group are not insignificant. Within our immediate neighborhood, the local group, our galaxy, is one of the dominant members. Its gravity shapes the motions of dozens of smaller galaxies. Its dark matter halo extends for hundreds of thousands of light-years. Its satellite galaxies orbit faithfully in the surrounding space. Within a radius of a few million light-years, the Milky Way and Andromeda are the gravitational anchors of the region. They dominate their corner of the universe, even if that corner is small by the standards of superclusters and cosmic webs. This layered structure, a planet within a solar system, within a galaxy, within a local group, within a supercluster, within the cosmic web, is one of the most beautiful discoveries of modern astronomy. The universe is not uniform. It is not a smooth, featureless distribution of matter in space. It is structured on every scale, with matter organized in hierarchical layers of increasing size. Planets, stars, galaxies, groups, clusters, superclusters, filaments of the cosmic web. Each level is embedded within the next, each organized by gravity into coherent, bounded structures. And everywhere within this hierarchy, the same story plays out. Matter gathering together under the influence of gravity, forming structures at whatever scale the local conditions permit, each structure becoming the building block of the next level up. The universe builds upward from the smallest scales to the largest, assembling complexity from simplicity through the patient application of the same basic force that holds you against the earth as you lie here tonight. There's something grounding, literally grounding, in this picture. Gravity operates on every scale in the universe, from the pull that keeps your feet on the ground to the force that holds galaxies in clusters and clusters and superclusters. The same force that shaped the Milky Way into its disk, that holds your body against the Earth, that keeps the moon in orbit and the planets circling the sun. It operates across every scale, linking the smallest and the largest, weaving the universe into a coherent, connected whole. You are held by the same force that holds the Milky Way in the local group, that holds the local group within the Virgo supercluster, that shapes the largest structures in the observable universe. Gravity does not stop at the boundary of the solar system, or the galaxy, or the local group. It reaches outward indefinitely, growing weaker with distance, but never quite reaching zero. You are, in the most literal sense, gravitationally connected to Andromeda, to the Virgo cluster, to the galaxies at the edge of the observable universe. The connection is tiny, infinitesimally small at those distances, but it is real. You are part of the largest structure we know. You are embedded in Laniakea, in the Virgo supercluster, in the local group, in the Milky Way, on a small planet orbiting a modest star. Every layer of that embedding is held together by the same force that holds you in your bed tonight. Rest in that connection. Rest in the vast, patient, gravitational embrace of the universe. We have arrived at the last chapter, the final chapter of this long, quiet journey through the Milky Way. If you have been drifting in and out of sleep, if these words have been reaching you from far away, like starlight through a half-open window, that is exactly right. That is exactly where you should be. But if some part of you is still awake and listening, still following the thread of this story through the dark, then stay with me a little longer. This last chapter is the one that brings everything together, the beginning, the middle, and the long, open future of the galaxy we call home. The Milky Way began very close to the beginning of everything. The universe is approximately 13.8 billion years old, and our galaxy began forming not long after, within the first few 100 million years of cosmic history, when the universe was still young and hot and churning with the energy of its initial expansion. The first structures to form the young universe were not galaxies, but something much simpler: dark matter halos. Regions of slightly higher density in the dark matter distribution of the early universe began to collapse inward under their own gravity, drawing material together and creating the gravitational wells into which ordinary matter, hydrogen and helium gas, would eventually fall. The Milky Way grew from one of these dark matter halos. Gas fell into the gravitational well, slowly at first, then more rapidly as the halo accumulated mass. As the gas fell inward and compressed, it heated up, and eventually it reached conditions where stars could form, the first stars of what would become our galaxy, igniting in the dense, hot cores of collapsing gas clouds in the early universe. These first stars were very different from the stars we know today. Massive, brilliant, and extremely short-lived, containing almost no elements heavier than hydrogen and helium, because the universe had not yet had time to produce them. They burned furiously and died explosively, scattering the first heavy elements into the surrounding gas, and setting in motion the long cycle of stellar chemistry that has continued ever since. The early Milky Way was not a single, unified structure. It was a collection of smaller protogalactic fragments, clumps of gas and stars, each one embedded in its own dark matter halo, each one forming stars at its own pace. Over time, these fragments fell together, merging and combining under the influence of gravity, gradually assembling the larger structure that would become the Milky Way. The halo stars and globular clusters we explored in earlier chapters are largely survivors of this early, chaotic period. Ancient objects that formed in the protogalactic fragments before the disk had assembled itself, now orbiting in the halo as fossil remnants of the galaxy's earliest stages. The thick disk formed during a particularly active period early in the galaxy's history, a time when the rate of star formation was much higher than it is today, when large amounts of gas were falling into the growing galaxy from the surrounding environment and being rapidly converted into stars. This burst of star formation enriched the gas quickly with the alpha elements produced by massive star deaths, giving thick disk stars their distinctive chemical signature. And then the pace slowed. The most intense period of formation gave way to the quieter, more sustained star formation of the thin disk, the mode that has continued at a rate of roughly 1 to 2 solar masses per year for most of the galaxy's subsequent history. Growth has come not just from star formation in place, but from the accretion of smaller galaxies. The Milky Way has consumed dozens, perhaps hundreds, of smaller systems over its history. Dwarf galaxies and globular clusters absorbed through tidal disruption, their stars scattered into the halo, their dark matter merged into the larger halo, their chemical signatures mixed into the Milky Way's population. The stellar streams we discussed in earlier chapters are the traces of these past mergers, written in the halo in faint ribbons of stars that preserve the orbital signatures of long-gone satellite galaxies. The Milky Way has been built partly from within and partly from outside, assembled through the patient accumulation of smaller structures over billions of years. And this assembly is not complete. Accretion continues today. The Magellanic Clouds, those two bright satellite galaxies visible from the southern hemisphere, are in the process of being drawn closer by the Milky Way's gravity, their gas streaming away into the Magellanic Stream, their stars beginning the long, slow process of tidal disruption that will eventually incorporate them into our galaxy. The Sagittarius dwarf, already significantly disrupted, continues to lose stars to the Sagittarius Stream with each orbital pass through the galactic disk. Smaller, dimmer dwarf galaxies continue to orbit, their ultimate fate determined by the slow grinding of tidal forces over millions of years. What of the future? What does the long, patient destiny of the Milky Way look like if we follow the story forward billions of years rather than backward? The most dramatic event in our galaxy's foreseeable future is one that has been confirmed by precise measurements of galactic motions. The Milky Way and the Andromeda Galaxy are approaching each other. The two dominant spirals of the local group are falling toward each other under the influence of their combined gravity, closing the gap between them at a rate of roughly 110 kilometers per second. At this rate, Andromeda and the Milky Way are expected to collide, or rather, to begin their first close encounter, in approximately 4 to 5 billion years. The word collision is somewhat misleading, because the stars in a galaxy are so widely spaced that a direct physical collision between individual stars is extremely unlikely even when two galaxies pass through each other. What will actually happen is more like an interpenetration. The two galaxies will pass through each other, their stars following complex new gravitational trajectories as the two systems interact, and then, after separating and falling back together again in subsequent encounters, they will eventually merge into a single, combined galaxy. The merger of the Milky Way and Andromeda will be a spectacular and prolonged event by any measure, though no human civilization will be around to observe it in its entirety. The process will take several billion years to complete. During the merger, the orderly disk structure of both galaxies will be disrupted. Stars will be flung into new orbits by the combined gravitational influence of the two merging systems. Gas clouds will collide and compress, triggering bursts of star formation. The shapes of both galaxies will be distorted and transformed, their beautiful spiral structures broken apart and rearranged into the new configuration that the merged system will eventually settle into. The likely end result, based on computer simulations of similar galactic mergers, is a large elliptical galaxy, or something like an elliptical, very different in character from either the Milky Way or Andromeda today. Elliptical galaxies are smooth, featureless, roughly spherical or ovoid systems, lacking the disk and spiral arms that make spiral galaxies so visually striking. They tend to be dominated by older stars, having consumed or expelled most of their gas supply and settled into a quieter state of diminished star formation. The merged remnant of the Milky Way and Andromeda, sometimes called Milkomeda or Milkdromeda by astronomers who enjoy a certain kind of whimsy, will likely be such a system, a great elliptical galaxy containing the combined stellar populations of both progenitors, orbiting on through the long future of the universe. By the time this merger occurs, our Sun will have long since ended its main sequence life. In about 5 billion years, conveniently, roughly the same timescale as the Milky Way Andromeda merger, our Sun will exhaust the hydrogen fuel in its core and expand into a red giant, eventually shedding its outer layers into a planetary nebula and leaving behind a dense white dwarf. The Earth, if it survives the Sun's red giant phase, will no longer be habitable. Whatever life exists on Earth or elsewhere in the solar system will have had to adapt or perish long before. The merger of galaxies will happen against a background of stellar evolution that, on our own small world, will have already fundamentally altered the conditions for life. And yet the universe will continue, long after the Sun's death and the galactic merger. The stars that formed during and after the Milky Way Andromeda merger will burn on for billions or trillions of years. The low-mass red dwarf stars, the most common type in the galaxy and the longest lived, will continue burning for hundreds of billions or even trillions of years, long outlasting stars like our Sun. The merged galaxy will be home to new generations of stars forming from the gas remaining after the collision, and to old stars, some perhaps containing worlds, that will persist long into the deep future. The story of the Milky Way, in this sense, is not a story with an ending, or at least not one visible from where we stand in time. It is an ongoing story, one that began nearly 14 billion years ago in the collapse of gas into a dark matter halo, that has continued through generations of star formation and stellar death, through mergers and accretions and chemical enrichment, and that will continue through the merger with Andromeda and beyond, into a future so distant that our imaginations can only gesture toward it. And somewhere in the middle of that story, not at the beginning, not at the end, but in a particular moment of a particular era, on a particular small planet orbiting a particular medium-sized star in a quiet spur of a spiral arm, you are here, breathing, resting, having traveled, tonight, through the history and structure and future of the galaxy that contains you. The Milky Way began as gas and dark matter, assembled itself through billions of years of star formation and mergers, produced the Sun and the Earth and the conditions for life, and eventually produced you, a being curious and patient enough to lie in the dark and listen to its story. That is not a small thing. The universe has been working for nearly 14 billion years, And one of the things it has produced is you, tonight, resting in the knowledge that you are part of something ancient and vast and still unfolding. The galaxy is not finished. The story is not over, and you are part of it. Not a spectator, not an observer standing outside looking in, but a participant, made of its matter, carried by its motion, existing within its long, patient story. Let your eyes be completely closed now. Let your thoughts be as soft and as diffuse as the halo of the galaxy, spread wide and thinly through the dark, not grasping anything, not holding on to anything. The Milky Way turns slowly above you and below you and around you in every direction. The ancient stars of the halo keep their long orbits. The central black hole waits at the heart of the galaxy, quiet for now. The satellite galaxies trace their paths through the halo. Andromeda, 2.5 million light-years away, approaches at its 100 kilometers per second, closing a gap so vast that the approach feels like stillness. You are inside all of this. You have always been inside all of this. The galaxy has always been your home. Not just tonight, not just in your lifetime, but in every atom of you that has ever existed, stretching back through generations of stars to the earliest moments of the galaxy's formation. You are the Milky Way's current, most intricate expression, briefly conscious, briefly aware, briefly capable of wondering about the home that made you. Sleep now. Rest in your ancient, luminous, slowly turning home. The galaxy will still be here when you wake. It always has been. It always will be. Good night.